Okay, with that in mind, let's go ahead and get started. As I said, today is the one day that spilled over, or yesterday's the one day that spills over a little bit just because we packed a little bit too much in that agenda. I anticipated that, and it's no big deal because today's agenda is a little bit light because we're going to find out there's so much overlap between OpenMP and OpenACC that you've already learned an awful lot of how to use the GPU programming approach OpenACC we're going to use today. So with that said, let's finish up yesterday's OpenMP topic in a more leisurely pace instead of the panicked cram it in the last 10 minutes fashion that we would have done yesterday. So we'll pick up where we left off yesterday with exercise 2, which was improving our prime number generator. And the main motivation for this exercise is that we covered a lot of advanced OpenMP at the end of yesterday just to expose you to all the capabilities that are there. And I know it can't help but intimidate you some to say, oh my God, there's all this complex stuff out there. And in particular, when I started to talk about deadlocks and other kind of race conditions that can come up when you take that low level control, you can't help but start to think that these are pitfalls that you're going to encounter when you're working on your normal scientific codes. And that's not true. As I said, and as I can't emphasize enough, the toolbox that we assembled for the first exercise, which was mostly the parallel for, the parallel dupe, and some private variables and some reduction variables, will serve you very well for many of you over an awful lot of codes to accelerate your codes in a safe way that doesn't have a lot of dangerous traps hidden in it. So if you just hold on tenaciously onto that set of tools right there and realize all the advanced stuff that we talked about are kind of optional extensions that some of you may find useful or even critical, but that are not the essential things that you have to use all the time. Then you won't be too scared about the fact that OpenMP has a lot of low level stuff. So this exercise here is to illustrate some of the higher level optimizations you can do that aren't at all frightening in terms of they're not introducing a possibility for errors to creep into your code. In particular, we had our prime number solver, which was this very simple-minded way of finding prime numbers here. Not the world's most effective algorithm, but very easy to understand one. And we parallelized it with the parallel for, and that was all we needed to do. And we got and the reduction, a proper reduction, and we got good results. And that was exactly, it was a good example of the kind of easy, quick application of OpenMP that can bear great fruit. And then when we're talking about the more advanced OpenMP stuff, I pointed out, and also a number of questions came into the chat channel saying, well, what about if the amount of work done by each one of the threads is different? Isn't that going to cause some of them to waste time sitting there? And for our Laplace code, we can imagine when we break up the metal plate into, say, 10 strips with 10 threads, that the amount of work is pretty balanced. It's not the kind of thing we need to worry about there. So we wouldn't worry about that there. On the other hand, with our prime number finding code, we can imagine that some of these iterations take a lot longer than others. If there's a very large prime number, like let's pretend that 200,043 is a prime number. If that's the case, then the PE that's looking, or the thread that's doing that work, has to go through 200,043 iterations to find out that that it's a prime number. Well, if another PE is looking at the number 4, it doesn't have much work at all to do to figure out that it's not a prime number. All right, so these threads are going to take different amounts of time for each one of these number checks. So maybe here we might want to have a more sophisticated scheme than just give the first thread 50,000 numbers and give the next thread another 50,000 numbers. And indeed, it's very easy in OpenMP with the clauses that I presented to you here to add on to our parallel loop some options like this, like schedule dynamic. This is the one that I found to be effective. I threw schedule dynamic on here, and schedule dynamic says instead of breaking up all 500,000 numbers across each one of the PEs evenly, so give, say, 10 threads, give each one of them 50,000 iterations. Instead of doing that, let's instead, with dynamic as it stands right now, let's have each thread take one number at a time and go through it. And so if one of them is taking a long time, the other PEs that have less work to do because they got the easy numbers can jump in and do more easy numbers. So this dynamic scheduling right here worked out pretty well for me, and I ended up speeding things up still by another factor of 2 or so. Overall, together, it was 63 times the original serial code. So that's the huge win right here. This is 63 times faster than the serial loop, but it sped things up by about a factor of 2 over not having that clause there. So these are the kind of nice safe optimizations that you can do in OpenMP. And furthermore, you can see how painless they are to experiment with. So if you've taken weeks or months, or in some cases years, to write a code for your research work, isn't it awesome that OpenMP allows you to come in and do some experiments in an afternoon to not only parallelize your code, but also play around with optimization like this that only take, minutes to do. So you can really play around and experiment. And these are very low risk things. The things we talked about with the advanced OpenMP at the end of yesterday seem a little bit complicated, because they are, and they take usually some experience and some thought to use effectively. But these kind of tools right here are not. They're low risk. They're easy to experiment with. Nothing to lose experiments. You try them, and if they work, you've sped things up even further. And if they don't, you say, well, that took me 20 minutes, which is a small amount of time to spend on a code, like I said, that might have taken you days or weeks or months to write. So that, I hope, is the philosophy you take away from our OpenMP here, is that you wrote a code, you're working on a project, your research code, you've got a lot of time and effort invested in it, and OpenMP allows you to come in and in an afternoon try some OpenMP, in a matter of minutes even, try some experiments with that OpenMP and see if you can make it even better. So it's a painless way to do this stuff. And we'll see as we go through this week, especially as we get to MPI, life isn't always that painless. Some things require a lot more commitment and effort, in order to parallelize your code. But with OpenMP, I hope you feel emboldened to try experiments and do things. So I didn't want to rush this at the end of yesterday, as we were kind of running out of time, because it's an important moral to take away from OpenMP. It's a painless, quick way to try things. And in the end, with this code, for example, it runs 63 times faster. That's not insignificant. Okay, we got some questions streaming in here. Let's see. Yeah, some people are suggesting some optimizations for the prime number finder. Yes, that's very easy to do. This is the most simple-minded version I could write. And I guarantee you that if you go down that rabbit hole of how to find prime numbers, it's fascinating and interesting excursion into number theory. And it's endless and bottomless, and currently still a hot area of research. So this is far from the smartest algorithm. And some of you tried some other things, guided versus dynamic, and there are chunk sizes. I should point out, this is not the definitive answer. If we look at the alternatives I suggested you try here, some of these other, for example, there are chunk sizes. I didn't try, maybe I did, different chunk sizes with dynamic, which means instead of giving one thread as it comes back and it says, I'm done, give me some more work, instead of giving it one iteration, you could say, give it 5, give all the threads 5 iterations at a time to work on. And that cuts down on the overhead of it having to do all that bookkeeping, but makes it a little bit coarser in terms of the amount of work it's biting off. So there's lots of ways to play around with this, and I wouldn't be surprised if, based on a different compiler, because different compilers do things slightly differently, you could come up with a better solution than I do. If one of you comes up with something that works significantly better than I have, please, I'd be delighted to use it as the future recommended or best found solution. Let's see. Can I explain again how the schedule is working? Okay, I don't know if that question was sitting there long enough that I did or didn't, but I'll say it one more time for everybody. It can't hurt. The idea here is basically, with the standard way that we start out with static scheduling, is that when we've got, if this loop has 500,000 iterations, that's what n is equal to here. You don't see that part of the code up here, but 500,000 iterations, and we have, say, 10 threads working on this. The static way of doing this would be to give each thread 50,000 iterations from the get-go. So thread 0 would have iterations 0 to 449,999. Thread 1 would have 50,000 to 100,000, basically. And so that would be a way to break them all off in advance. But you might well imagine that the thread that has the lowest numbers has the easiest amount of work to do. And so instead, we can say, and it would get done quicker and just sit there and waste time. And the thread with some of the larger numbers might be the thing that holds us all up. So instead, we can choose to do things in a more dynamic fashion here. And that says each thread does one number at a time, and then come back and ask for the next number that's not being worked on yet. So that's dynamic. And we can do it in chunks, and we can do it in various guided fashions, which means each block shrinks down in size as you go. So those are options. And again, the important thing to take away is that OpenMP has lots of ways to tweak and optimize things that are painless. You can just throw them on the end of these clauses and see what happens. Okay. Are there modes or additional software allow you to see how many nodes or threads are actually being used? Absolutely. So one of the things that we've taken, so you've taken for granted so far, and I'm just explaining how things work here. How do you actually, confirm this or check this out? Or in particular, when you're doing optimization like this, how do you How do you dive into it more and find out whether your threads are wasting time? And that's where profilers come in. And I don't want to mix tools because they're very tool specific kind of details into the talks just yet. So I saved those for the end. So at the end of the week, we have a tools talk, and I'll talk about profilers and debuggers, two things that if we had experience with them, we'd be using throughout the week to work on these exercises. We use debuggers to find errors in our code, and we use tools like profilers in particular to find out where our codes aren't running well, where they're not parallelizing well, or where you might want to focus on parallelizing your codes. But again, since I don't want to get us, we're already learning an awful lot of fundamental stuff here. I don't want to get tools mixed in here, but they're very important and it'd be silly not to use them. So if this were really a larger, more complex code with a lot going on, I would immediately get a profiler involved here as I try my different optimizations, and it would tell me, hey, these threads are sitting here. It would show me threads that are done early. And modern profilers are very nice. They've got nice GUI, nice graphical interfaces, and they'll say, hey, this subroutine here, you can see how many wasted idle cycles your threads have because you don't have things load balanced well. And it gives you a good idea where you might want to start trying some of these alternative optimizations. So we'll get into the profilers at the end of the week, but there are great tools to do that. So you don't have to just depend on experience and intuition. Let's see. Explain what the chunk size is and how we can find an optimal value for it. So the chunk size, I think I probably explained this for everybody, is how many pieces you bite off at a time instead of it asking for one more iteration to work on. Every thread that goes back as it's done will be given, say, 5 if you say a chunk size of 5. And how do you find the optimal value for it? Experimentation. This is where empirical playing around with it is undoubtedly the smart way to go. Sitting down with your pencil and paper and trying to analytically find it would be silly. Instead, you just empirically try some different chunk sizes and see what happens. And it's so painless to do here that that's the way that experts will do it, is empirically. They will not sit down and think that they're going to analytically determine the optimal value. So do it with a little bit of experimentation. And again, if you've taken weeks or months or years to write a code, spending 15 or 20 minutes experimenting around is not a bad trade-off. With this program, is it correct to say only the outer loop is parallelized? Yes, that is true. With OpenMP, by default, only the outer loops get distributed amongst the PEs. Now, you can change that with the collapse clause we mentioned yesterday in the case that your outer loop is very small. So if your outer loop happens to be like, go 1 to 3, and it's not impossible to have a code where the outer loop might go 1 to 3 and the inside loop might go 1 to 10,000. In that case, you could use the collapse clause, and then the compiler will go and combine the 2 loops together for you and give you more work to spread around the PEs, because by default, it will only parallelize spread around the outermost loop. Okay, that's the next question. Okay. What is the downside of using dynamic as compared to static? It does add some overhead. With static, life is very simple, and it just says, here, thread, go off and work on these 100,000 iterations. With dynamic, the thread has to do some work and then come back and check. So dynamic does introduce some overhead. Whether that overhead is worth it or not depends on the kind of load imbalance that's going on. So with our Laplace code, it's not going to be a win because it's such a regular amount of work with us scanning over our metal plate and just doing these very regular calculations. So with the Laplace code, dynamic's not going to do anything but introduce some overhead. With this number finding thing right here, prime number finding, where there's vastly different amounts of work depending on whether a number's prime or not, it's a win. It's a big win. Which memory keeps track of head count or bookkeeping? Well, that's the compiler. Nice thing about OpenMP is the compiler has to worry about all those mechanics on its own. So somewhere off to the side, the compiler's runtime mechanisms do all of the scheduling and management for you. And it's very well optimized. And one of the things that the standard's careful to do is not introduce things that can take a lot of memory. So all the things that OpenMP does for you, as smart as they are, they're not things that could require a ton of memory or become explosive in terms of overhead. So that is, there are certain capabilities they just forgo. They don't introduce because they recognize that they could potentially involve a ton of, they need a lot of memory to work or something like that. They make copies of variables automatically or something. So with OpenMP, it keeps track of all this stuff in its own scheduler here. And that's a kind of thing that's been optimized and is very lightweight. So it doesn't take a ton of memory, so you don't have to worry about it. Okay, I think I've caught up with the questions with that. Okay, so again, the results are spectacular in terms of the overall increase, certainly 63 times, and the speed up with the optimization is a pretty nice factor of 2 as well. So, okay, let's cover the last couple of details about OpenMP. These last few slides is one of the things we didn't mention is that there are a lot of environment variables. For, again, those of you that are comfortable in Unix type shells and environments, no environment variables, there are lots of them floating around. If you want to see what's going on right now, if you type printenv, P-R-I-N-T-E-N-V, you can see there are a bunch of environment variables in all of our environments that keep track of, whatever different programs and you want to keep track of. And OpenMP has its own handful of those that allow you to manipulate behavior as well. So you can set these environment variables outside of your program. One that we've obviously been using is OMP num threads. We've been using that a lot. It's very, very basic to what we're doing here to control the number of threads that get launched when you run. But there are also more subtle behaviors that you can, you can say limit the number of threads. We can see the default here set to some very large number. And so there are other things that you can set with the environment variables as well. So be aware of that. The defaults are going to be fine for all of you. So the only one you really have to be aware of basically is OMP num threads. That's pretty important. But you can see there are other ways to change the behavior of your code from environment variables as well as within the code itself. So I just want to make you aware of that. And we had more than a few questions about C++. And I want to point out that C++ operates extremely well with OpenMP, not just in the C mode, which is true a lot of times. If you're in C++, you should never hesitate to grab anything that's done in C because you know it interfaces pretty well. But OpenMP also accommodates actual C++ characteristics. Like, for example, it works just fine with objects, but you need to be aware of what you're doing. So if you have an object, constructors and destructors are called if you make private copies. They have to be, right? It's the only way to create an object sensibly. So be aware of you don't really have to, if you understand how C++ works, all these things seem almost inevitable, but you do need to be aware of them. So you can use objects anywhere that you can use regular variables, except you need to be aware of things like the constructors are called. But what about with first private? Things you got to think about it a little bit, and it starts to get a little bit complicated. So you need to be aware of these things. The biggest question I get typically from people that are C++ users is people like to use standard vector as a replacement for arrays, multidimensional arrays. And you have to be very careful with that in general, not just with OpenMP, because a vector of vectors is not the same as a two-dimensional array. It is not contiguous in memory. And so it's performance-wise, it's a big issue, and passing around a vector of vectors as though it's a two-dimensional memory array to a GPU or something like that does not work. So you need to be aware of what an actual vector is. And a part of the wonder of C++ containers is it's supposed to isolate you. It's the big trade-off in C++, right? Is the containers are supposed to isolate you from having to know the details. That's one of the good things, right? You don't worry about what a vector really is inside. On the other hand, sometimes it's necessary to know what's going on inside. And certainly that's true when you start doing things like sending a vector off to a GPU or using it with threads, multiple threads and things. And so you need to be aware that of what's going on. And other containers, for example, are even less likely to work. For example, a standard list, which is just a doubly linked list, using a bunch of threads on that without locking it properly would be a very bad idea. So you need to, you need to actually know what the containers, the STL, containers are if you're going to use them effectively in high performance computing in general. It's not an OpenMP issue, it's just a performance oriented issue. But that shouldn't be a completely new issue to you if you're using C++ and for high performance or for numerical computing. And we'll talk about later on, MPI has actually dropped C++ as the standard interface to MPI because of some of these issues. We'll get back to that. But don't panic yet. It works just fine with the C interface. And again, if you're a C++ person, you should be used to using C code and with the standard C interface. Let's see. Oh, here's an AWS outage is causing Zoom issues. That is not good news. Let me see how bad this is and how much we might want to bend to what we can do.
We've had a few complaints, John, of dropped connections. I'm not seeing it here. I don't know if Steve is, but it seems like when I looked on the Zoom pages, there are a number of people reporting issues at the moment.
That's good here.
Okay. Yeah, I actually saw on the news yesterday that a big CDN had problems, and yeah, half the internet was blipping for yesterday morning, including AWS. Okay, well, we'll, in lieu of any better plan, we'll forge ahead then. Okay, so that's it for OpenMP. And again, if it seems like there's an information overload here, because we did cover the entire, basically we covered everything about OpenMP, including all the advanced stuff. But again, hold on to the first part of our talk yesterday, where we basically said, hey, for the big for and do loops, you only need a small subset of these tools and you can be very, very effective, because for most of you, that's going to be as far as you need to go to get some great results. So don't be scared off by all the advanced stuff we covered. On the other hand, be aware that it's out there. So if you do find yourself writing some, graph algorithm and it has a recursive, it's just naturally a recursive algorithm, and you go, well, how do I make that work with a parallel for loop? And the answer is you wouldn't do that. Instead, you'd use tasks. Or if you find yourself saying, I've got a bunch of data structures that I need to manipulate with multiple threads, and I look at somebody says the way to do this is to use locks on these data. You go, okay, well, OpenMP can deal with that. So be aware of all the capabilities, but don't be intimidated by them. And so I'm glad we covered everything, but I also recognize that it can scare people away and make them think that they have to master all of OpenMP before they can get good, effective results. And nothing could be further from the truth. You can get great results starting out with just the basic parallel for and do loops. So, and let's see here. Okay, so let's go ahead then, and with that, and move on to our proper agenda for the day, which is OpenACC, which might seem like, if you don't know anything about it, might seem like a jump in a very, very different direction. Whoops, I don't want the advanced talk here. But instead, turns out to be a lot of deja vu. It's going to seem very similar to what we did yesterday. Now, fear not, I'm not going to be redundant. I've taken the opportunity to leverage what we learned yesterday to speed up this topic an awful lot. But you're going to find that there is, we could eliminate. We don't have to learn a lot as much as we would if we were starting from scratch, because OpenACC builds an awful lot upon what we covered yesterday with OpenMP, and it's not a coincidence. Okay, good to go here. So OpenACC's definition, yesterday we started, I said, let's just do the short definition of what OpenMP is and then see if we can pull it apart. Well, we'll do the same thing with OpenACC. OpenACC is a directive-based standard to allow developers to take advantage of accelerators, such as GPUs from NVIDIA and AMD and Intel and other manufacturers as well. Okay, well, when I say accelerators is the generic term, and you'll find the documentation, the OpenACC documentation, as well as other documentation, uses a lot when it just means GPUs, because most accelerators in the world by far are GPUs, these repurposed graphics cards. This whole thing springs from the fact that yesterday I mentioned in the intro to parallel computing that people noticed in about 20 years ago that GPUs gave you a lot of floating point operations for cheap dollars. On paper, at least, because just in the process of rendering video frames, of making your favorite video game run at 60 frames per second, that it was doing a lot of math. And so very heroic scientists said, boy, if we could repurpose this math for our own scientific codes, we might have a cheap way of getting a lot of flops. And indeed, that was a great idea. NVIDIA was the first to really jump on the bandwagon and support it. Instead of having to do these ridiculous things and jump through these crazy hoops to basically repurpose video shading code to make it do science, we'll give you at least some way, and it was called CUDA, some interface to the video hardware that's a little bit easier to just pump math through. And so NVIDIA supported it, and as a result, they have dominated the market. And so when people say programming with GPUs, they're talking usually about, I've got some NVIDIA card and I use it, but it actually is a broader thing. And the term that is used again in the documentation to be neutral is accelerators. So you'll hear people talk about accelerators. And again, 90+% of accelerators are GPUs, and a fair number of those are NVIDIA, but AMD also makes competitive GPUs. Intel had a line that was that was different, but still an accelerator for a while, called Xeon Phi. We'll talk briefly about this at the end of the day. They've since dropped this, but now they're back to making a more generic accelerator, which is in the newest exascale machines that I pointed out yesterday. So if you go back and look at the exascale machines, or that top 500 list we were reviewing yesterday, you'll see a mixture in there of all of these. And then there are also, I mentioned in the intro to parallel computing talk, there are people these days doing important work with field programmable gate arrays, or basically programmable hardware or digital signal processing chips. And OpenACC also gives them the ability to program those chips at a higher level. So although 90+% of you are just going to use this to run on GPUs, I'll be using the term accelerators as much as possible today to be kind of neutral. So when you hear the term accelerator, it means, or when you read it in the documentation, you can think GPU. Now, directives, this is the directive-based approach. So we have directives again. Well, the reason is that directives were so wildly successful with OpenMP that when people were casting about for a higher level way than CUDA to do this stuff, because CUDA was an expedient way to get things off the ground. It was the first shot when there was nothing else out there, and so people adopted it and made it work. But CUDA is terribly, terribly low level and extremely platform and version dependent, which is even worse in an area like GPUs, where every couple of years the hardware advances a lot, and all of a sudden the CUDA interface to it changes a whole lot. So for maintainability, CUDA is a nightmare. It's not fun to use because there's so much boilerplate, the stupid kind of stuff. You go, why isn't the compiler doing this for me? So after CUDA became popular because it enabled people to use these GPUs, people said there's got to be a better way. And indeed, they said, look at what OpenMP did to make, to get rid of p-threads, nonsense. So much easier to use OpenMP than p-threads. Can't we do that here? And the answer is yes. And so, as we'll talk about in more detail later, the OpenMP committee said, okay, let's spin off a separate standard so that they can work on this fast. Because OpenMP is very, very widely used and adopted. So you can't let people really evolve the standard quickly and nimbly, because there's too much depends on OpenMP. So instead they said, let's spin off this new standard, and that way it can evolve very quickly. You can change from version 1 to version 2 in a matter of a year or two to get as we're learning. And so that's what OpenACC is. So it looks an awful lot like OpenMP for a good reason. And it brings us the same benefits. And so as OpenMP programmers, you're going to be, like I said, we've already learned an awful lot of OpenACC approach. Not all of it, there are some differences. There's a reason that OpenACC is its own separate thing. And we're going to find that out very quickly here, that we have our own concerns. But you might ask, how else could you use GPUs? So we do have CUDA, as I've mentioned, which is the low-level thing. It's kind of the machine language version of GPU programming. And it gives you the maximum flexibility to talk to the hardware at the lowest level, but just like machine language, it's painful to use. A lot of times it's not buying you anything over using a compiler, and most importantly, maintainability is really a nightmare because the hardware is advancing so rapidly. It'd be like trying to use machine language back in the 50s and 60s when the hardware was changing all the time, and so your fundamental instruction set was changing all the time. It was very, very painful to do low-level programming back then in a portable way. We're going to use OpenACC, and it's going to be great. But we find out also there are a ton of libraries out there. And anytime there's a library that does what you want to do, or a substantial portion of what you want to do, it's silly not to use it, because quite possibly, not only does somebody doing your work for you, but quite possibly they've done it in a really optimized way, using clever techniques that you're never going to, utilize yourself, and you hope it's bug-free. So there are a lot of great, robust libraries out there, and it's silly not to use them. And that's true in the GPU computing world. Most of those libraries are written in CUDA. People over the past 15 years done a whole lot of very good work to do things like sorts and linear algebra things and searches and stuff you wouldn't even have thought of. We'll look briefly at, we'll do a little survey of the libraries that are out there. But if you look at any algorithm and Google, GPU version of it or CUDA version of it, you're likely to be pleasantly surprised that somebody's made a library. So it's silly not to use those. The nice thing about OpenACC, it allows us to use these libraries, most of which are CUDA, in a very simple, friendly way. As a matter of fact, this is such an important topic that I've even broken it off as a separate talk. You'll notice in the agenda today, we have using OpenACC with libraries, and that's because you don't want to overlook this option, and it's very easy to do. So it's a short talk, but I think it deserved its own space. But we're going to focus on writing our own CUDA, or excuse me, our own GPU code here with OpenACC. And once again, the advantages of this looks like a very similar list to OpenMP, because it is bringing in the same advantages. It's going to be high level. We're going to be able to stick with our single source. Once again, just like with OpenMP, we're not going to have to fork off our serial code. We're going to add these directives in, and somebody that doesn't know anything about GPU programming can just ignore them, and they can still see what the algorithm does. Efficiency. I'm going to take a couple of slides to talk about this, because you should always be suspicious when somebody's telling you that their higher level, more productive approach doesn't cost you anything in terms of performance. That's usually not the case. Making life easier for the programmer usually means it's costing you somewhere along the lines in terms of performance. Maybe in a major way, maybe in a minor way, but anybody that's tells you get to use the easiest way to program, and also it'll be just it'll be fine for writing real-time control systems. Usually that's doesn't quite work out that way. Well, in this case here, It does, and we're going to find out, just like with OpenMP. With OpenMP, by the time your code's running, it's using the lowest level threading capabilities of the operating system, and there's really no performance penalty. We'll find out the same can be true largely with OpenACC. But I'll prove that to you a little bit before we get started. It'll be portable. Once again, the codes we're going to write here, we're going to run on Bridges GPUs, which happen to be, there are different kinds of GPUs on Bridges. We're going to be using the Volta ones ourselves, but it could run just as well on Ampere ones, or it could run on it could run on the GPUs that you happen to have in your laptop. And so the code's going to be extremely portable. And once again, we're going to go one loop at a time in our code. We're going to find the loops where all the work is done and accelerate those. And since we did that with OpenMP yesterday, you might be starting to get the notion that that's the standard way to do, that's a given. You can always do coding that way. That's not at all true. When we go to MPI, you're going to find out that life can be much more involved to do other tasks. And so the fact that we can do this incrementally, loop at a time, is great. This also is a standard, just like OpenMP is a nice open standard. So therefore, you don't have to worry about some vendor getting clever with things. And in the advanced talk today, we'll see how the vendors can make life miserable for people at times, and and dead end different types of approaches. And at any rate, we'll save that discussion for later. Suffice to say for now that the fact this is a nice open standard means you don't have to worry about about proprietary issues. And it does mean that compilers, embrace it, including GNU compiler. For a lot of you, the question is, can I get a free compiler that does this? And GNU's been doing this for a long time, since version 5. But if you do this with GNU, definitely use version 10 or newer, because this is, as I mentioned, a very fast moving field. GPUs are developing rapidly. So you want to use the latest versions of compilers. So you do not want to use an older GNU compiler. And a lot of people do by default use, older compilers. And that's fine for more mundane code, but for something that's as fast moving as GPUs, use GCC 10 or the newer versions. The compiler we're using is also available for free. The one that we're using, the NVIDIA compilers, as I mentioned, we're using them all week, but mostly because it makes today easy, because NVIDIA, no surprise, makes the best OpenACC compiler. For a long time, it was the PGI Portland Group compiler. They've renamed it since, in the past year or so, as the NVIDIA compiler. And so that's why our compilers that we've been using have been called NVC and NV Fortran. They'll be the best performance we're going to get for OpenACC. And you can get this compiler for free with their community version as well. So I don't think it's free for everybody. I think if you're a big industry or whatever, you have to buy a licensed version. The details are all right there. But there's a GNU version of it. Okay, there are a lot of resources at the openacc.org webpage, so you can get access to the compilers and tools and tutorials and everything else there. So if you get serious about this, it doesn't hurt to peruse their pages and see. There's been great adoption of OpenACC, so there's lots of things going on out there, including one of the things one of our users mentioned yesterday in chat was hackathons. So one opportunity, if you want to get intense and dive into this, there are these, NVIDIA's been hosting hackathons. Then they bring in outside expert staff, and and we kind of help people with projects work in a hackathon format, intense hackathon format. If the person mentioning their hackathon yesterday wants to throw the link up briefly in the chat channel here, this might be an appropriate time to do it. Because those are neat opportunities to really immerse yourself with your own code in OpenACC. So there's a lot going out there in the community. But I really want to focus on, before we get started, on the fact that there isn't a huge performance trade-off to do this, because this is so much easier than CUDA that people are sometimes skeptical. If you're a CUDA person, you say, okay, I've been dealing with this pain. Surely, there's a reason for it. It can't just be that the compiler can do all this for me. Well, the truth is the compiler can't. And if you do enough CUDA, after a while, the suspicion's the opposite. You go, this is such repetitive stuff. Why is it done at this low-level fashion? And so OpenACC does have lots and lots of success stories out there. And I always encourage people, before they make a commitment to a technology, to do a little investigation. Find out where people have really done real good work, finished work, not enthusiasm or, hey, this ought to work great. Find out where they've actually delivered results. And also try to find some horror stories. Try to find out where people said, this was a horrible waste of my time. I just wasted months and it was a dead end and we could never get it to work. That's those are the realities you want to be aware of before you start on something. So there are lots and lots of cases out there, and I won't go that are, good, positive things with OpenACC. I won't go through them, but I do want to mention one because it's a good example of the kind of concerns that you should have, as well as reaffirming that, that OpenACC is worthy of our time here. And that is where the government labs have, they have a lot of these big supercomputers. We saw on the top, 10 list, they have a number of machines there. So they have a lot of money invested in hundreds of millions of dollars in these platforms. And as a consequence, their codes that are their foremost concern on the machine have teams of people that work on optimizing them to run well on those platforms all the time. And as a matter of fact, they even have, for example, at Oak Ridge, where this code was run, they have an NVIDIA team in-house. They have people from NVIDIA sitting there full-time to help them optimize these important codes. And they have a very important code for them, S3D. It's a fuel combustion code. So it's a good example of a real complex code. It's not some simple, benchmark or something. And it does multi-physics, so it's got chemistry and thermodynamics and fluid dynamics and all kinds of things mixed together. So it's complex code, very important to them. And it was optimized to the utmost with CUDA by an NVIDIA team in-house dedicated to this and a handful of other codes. And so they knew what the performance was, but they also recognized, as did many people at the time, that the maintenance of CUDA code is awful. As every time you get a new generation GPU, it's tough, and it's in the way that the code forks off to be the CUDA version, looks less and less and less like any other branch of the code. So nobody's happy maintaining the CUDA versions of code. And so they were very attracted to the notion of using OpenACC. Only question was, are we going to trade off performance for it? Because again, they're running on machines that cost hundreds of millions of dollars. They are not willing to make that trade-off. They are willing to have the NVIDIA team in-house work as hard as they have to on the CUDA code, instead of making life easy on them by adopting something that's easier to program but has lower performance. So they did an investigation with this code that they actually published, which is the nice thing, because you can step through and look at it, where they said, okay, we're going to do the OpenACC port of this code. We're going to replace the CUDA with OpenACC in this code. And they did it. And this number of, the number of lines they had to modify for the code was not much at all. As we'll see with directive-based approaches, you saw with OpenMP, you hope you just go stick these directives in front of the big loops, and that's it. You don't have to change a whole lot. And indeed, they were able to do that. And they ended up, doing the full conversion, again, with the best expertise in-house, people that knew CUDA top to bottom, as well as OpenACC. And it ended up running at 15 petaflops, which is, at the time, was the fastest simulation of its type by far. Even today, this research is now, I guess, about maybe 6 or 7 years old. Even today, this is an incredibly fast code. There are very few codes in the world that run at this speed. And this is couple older generations of hardware. But they compared it then to their CUDA code. It ran within 1% of the CUDA code speed. And so this was what convinced them to invest heavily in OpenACC, and they since have. As a matter of fact, those hackathons we talked about, they regularly host OpenACC hackathons there, because their site is very invested in this. So this is a nice example of somebody who's very agnostic. They were willing to go either way. They already had the expertise and the ability to maintain 100% CUDA code. And they said, we're investigating this to see if it's really the way we should move forward with codes. And so it's good paper to read if you want to, see this kind of comparison. Great paper to read if you're at all interested in computational fluid dynamics in a multi-physics environment. So let's see. So let me back up and answer some questions here, since I see them streaming in. Can OpenACC be used on TPUs as well? No, TPUs are best used with TensorFlow. And this is because TPUs, and I assume you mean the proprietary term TPUs in Google. So Google TPUs are very tightly tied to TensorFlow, because that's Google's preferred framework. And TensorFlow is mostly dedicated to AI, to neural nets. So TPUs are pretty focused on neural nets, not generic scientific computing, and consequently, the way to program those is TensorFlow. It's a topic we'll get into more detail with in our machine learning workshop, but that's all I'll say on it here until we have a generic Q&A session. Let's see. Is it after NVC-MP, because A dot out was dash? Yeah, so I'm missing a question up above it. I assume it was A dot out. So A dot out, so when we're using the compilers, all compilers if you use, there's a -O flag, most compilers like, where you can rename your output file, but why clutter up our stuff with that? So I just let the compiler spit out its default output file, which is a.out. We've been using that for the past day, and we'll use it for the rest of the week. So if you use almost any compiler and you don't tell it to name the output file, it'll just dump out this a.out. The MP flag that we used yesterday, and we'll use a similar flag here, -ACC for OpenACC, is what tells it to make the multi-threaded version of it. So you get the same a.out, only one of them will be multi-threaded and the other one will not. And so if you have multiple a.outs sitting around, I rename them. So if I spit out an a.out and it's my multi-threaded version and I'm going to make some other files and screw around, I might just rename it to a.out to a.out MP, so it's clear to me. And renaming files is very easy, by the way. Those of you that are new to this, use the move MV command, MV. If you use MV, you can rename the file to anything else. And so you've got a lot of a.outs writing over each other that you can be confused as to which one's which, so you can start to rename them. Shouldn't be too much of an issue for the way we're doing exercises in this workshop. And somebody did basically answer what I just said. Let's see. Why are most deep learning libraries built on CUDA? Well, deep learning is, and again, we can't dive too deeply into it here, but deep learning, if you come to the deep learning workshop, you very quickly gain appreciation. The vast majority of deep learning is matrix multiplies. For again, reasons we won't dive into here, but so it's matrix multiplies. And GPUs, as we'll find out today, are fantastic at matrix multiplies. And so leveraging the hardware is important. And since CUDA libraries are sitting around that do great matrix multiplies, as a matter of fact, we'll use them ourselves. It's a great thing it's the natural thing to build most deep learning on top of. Let's see. Is CUDA an acronym? It is, and I can't remember what it is at the moment. It's been a long time since I've heard it said as anything other than CUDA. I want to say unified device. Well, Google it. So I'm pretty sure the unified device is part of it. But, let's see, NVIDIA showcase the. Let's see. I don't know what a DPU is at the moment, so I'd have to look it up and see what a DPU is. Oh, there we are. Compute Unified Device Architecture. How natural in that. Let's see. So there's the link for the NASA boot camp. So there's an opportunity. Like I said, lots going on in the OpenACC community if you want to jump into some more focused kind of events. Let's see. Oh, the name authors of the paper. Do I not have that here? Let me. I should. Yeah. Why don't I have the link here? I must have edited this slide to make life simpler. But whoops. Let me. Yeah. It's dumb of me not to have the link to the paper here. Hang on a second. Jeez. Yeah, I'm sorry. I edited the link for this. I'll find this and I'll post it in chat when we get to an exercise session, because that's dumb of me not to have it just prominently featured here. So yeah, I will do that. Okay, let's see other questions. Oh, somebody already posted it there. So great. Thank you for that. How does OpenMP compare with OpenACC in terms of performance? It will only run on the CPU. We'll come back to that at the end of the day. At the end of the day, you'll notice the last talk of today, which we'll have plenty of time to get to. Today's a much more leisurely schedule. Will be is our OpenMP on GPUs talk, and that's where we'll compare OpenMP and OpenACC and where they overlap, because there is some overlap. OpenMP has continued to expand to accommodate GPU computing as well, which brings up the question, well, why aren't we just using OpenMP for our GPU programming? Well, we'll answer that question at the end of the day. And the answer, the short version of it now, is that OpenACC is by far the superior way to program GPUs right now. But we'll get back to that topic. So we'll dedicate some time to that. We use OpenACC to parallelize on multiple GPUs. Yes, you can, but it does take a little more effort than I would prefer it to take, but you can, and it's very important these days. As a matter of fact, multiple GPU configurations have become the standard. On bridges, for example, all of our GPU nodes have multiple GPUs, 4 or 8 or more GPUs. And the idea, if one GPU is good, well, 4 or 8 is better. So you'll find most architectures these days where people have the money have more than one GPU per node. So it's increasingly important to take advantage of that, and we'll get to that. Okay, but let's actually start doing some coding here because that's where the fun part is, right? And so here's a very simple loop that we're going to use some OpenACC directives to accelerate. This loop, as simple as it is, this loop just takes one vector. Remember, vector is a term for an array here, one-dimensional array. Takes one vector and multiplies it by a number and then adds it to another. And so this simple loop, as simple as it is, actually has its own name, SAXP, because it shows up in, it's so important, it shows up over and over and over again that there are libraries, most linear algebra libraries actually have a library routine to do this. And you might say, why would you even have a library routine to save you from writing, 2 lines of code? And the answer is because that library even optimizes this better. Does all the right things in an optimal way. So simple-minded as this loop is, it has this name SAXP. And so scalar multiply x times y, whatever it stands for. So SAXP is a very simple loop, but we're going to run it on a GPU instead of running it on our CPU. And what we need to do that are just some simple directives. And again, the idea, so I don't have to go over this again, the idea is we're giving some hints to the compiler. The only difference between this and OpenMP is that our directives for OpenMP were called Pragma OMP, and then our directive, well, here they're called Pragma ACC in our directive. And likewise, instead of our Fortran directives being called bang $ OMP, here they're called bang $ ACC. That's the only difference. So it's the same idea. It applies in C to the next block of code. In Fortran, because we're on blocks of code per se, we have an N directive. Otherwise, they're the same directives. So if this looks very familiar, it should. And our kernels directive is the one that we're going to get a lot of work out of. Just like with OpenMP, we got a lot of work out of the parallel for or the parallel do directive. We're going to find that's even more true with the kernels directive in OpenACC. And we'll find out OpenACC is very flexible and powerful and can go low level. So we'll have lots of stuff in our advanced OpenACC talk. But we're going to find out that just using the kernels directive and the few things we need to add on to it is going to get us very far with an awful lot of codes. So it's going to be similar to using the parallel for and saying, okay, we need to do some privates. We needed to recognize a few things to make it work right, but that got us very far, right? Same with kernels. Our kernels directive is very powerful. And the kernels directive basically says, within whatever region the kernels directives apply to, whatever block of code you're applying them to, take any loops that are in there and move them onto the GPU. And so, and the term that you'll find used is they're called kernels. And this goes back to CUDA. So a chunk of code that runs on a GPU is called a kernel. And so it'll take and create kernels for each of the loops it finds in here. So this will go and create a couple of kernels that'll go and run on the GPU. And it's that simple, magic, right? That's the way that we hope directives work in the simplest best cases. And the syntax and scope is exactly the same as for OpenMP. It's just, again, the same thing we just talked about. And once again, I indent them in my examples here, which as they get more complex, you'll see more and more indentation. And a lot of people do not. They always left align them. That's strictly a matter of style. Don't worry about that. So here's our complete code. Here's the full SAXP. Here's a code that runs the SAXP thing. We won't pick it apart too much, but I do want to point one thing out that's a C issue. So the Fortran version, you can imagine, looks very similar, but we're going to point out one particular C issue here that's important. But we have this code here that created some arrays in C that, filled them up with numbers and then X and Y, and then multiplied it, use the SAXP loop. And all we had to do is throw kernels in front of it, and boom, the thing runs on a GPU and will run much faster. Now, there's one more thing in here, this restrict clause. It's not an OpenACC thing, but it's a very important C thing that a lot of people are not aware of. We're going to talk about. So I'll see a few questions popping in, but I'll wait till we get through this topic quickly. So the restrict command is something that's standard from C99, and yet many C programmers are not aware of it, even though it's probably the most important thing for performance you can know about C. So Fortran people, you could sit back and feel superior and ignore this for the next couple of minutes. But C people should pay close attention here, not just for OpenACC, but because if you're not using the restrict keyword in a lot of your C codes, you are missing out on an awful lot of performance. And the restrict keyword right here is basically a standard C. This is not an OpenACC thing. This is a standard C keyword. So it's been around since C99. It's been around for decades now. That basically says that this variable here that's referred to by a pointer, nothing else is pointing at this variable. And the reason that that's important is because in C, everything, especially arrays, everything's a pointer. And it is possible that this array that we're passing into to the SAXP routine right here, Y, could be also referred to by some other array. As a matter of fact, it's even possible that X and Y could really be the same arrays in disguise. The pointers could be pointing to the same thing. And if that's true, then we have all kinds of dependency issues that start to show up if we want to work on multiple chunks of X and Y. If X and Y are two normally completely separate arrays, which is what you'd normally expect, that's the same thing, right? X and Y are two different arrays. Then we can go off and grab a bunch of chunks of these and work on them separately. But what would happen if for some reason X and Y were pointing at the same array? These are pointers, it's possible. If X and Y are at the same array, then all of a sudden going and grabbing big chunks and working on them independently could cause problems, especially if one of them is overlapping. So maybe X is the first element of the array and Y points a couple elements down the array. And you start to try to work on these two things independently. You could have real problems. And so the fact that things can overlap in C means that the C compiler has to be very paranoid. And anytime it sees a situation like this, where all it knows is that X and Y are pointers to something, it can't do an awful lot of optimizations that it could otherwise do and probably should be doing. It has to always be crazy paranoid and assume these things overlap. So that's silly most of the time, the vast majority of the time, but a compiler has to be paranoid. It can't make assumptions and then deliver incorrect results. This is a huge handicap for C performance. As a matter of fact, when people often wonder, C and Fortran are the two highest performance languages typically in terms of, giving, fastest runtimes and results. And Fortran by default usually edges out C a little bit. And people wonder why it is. This is the main reason right here, is that in Fortran, it's assumed arrays never overlap. You don't have pointers floating around everywhere. Arrays are not allowed to overlap. They just aren't. In C, there's no such guarantee. So the compiler is very paranoid. And the way you can fix that problem is just adding in the restrict keyword and saying, I'm telling you, compiler, that nothing will ever overlap with Y, will ever refer to Y. And that makes all the difference in the world in terms of performance. Now, even in serial code, the compiler can use a lot of tricks like vectorization and run a lot faster. So C programmers out there, you should be using this restrict keyword all the time, all over the place, and your code will just speed up, just serial code. And it's important for our GPU code for the same reason if we want it to work right. So you'll see me using this restrict keyword here and there in our examples. You should be using it all the time in your C code outside of OpenACC or OpenMP. Okay, enough said about that. That's a C issue, not really an OpenACC issue, but I feel compelled to highlight it because it's just a lot of people see that and they're like, what's that restrict keyword? Not realizing that they should have been using it for years. Okay, that said, we have a very simple code here to compile it and run it is also very simple. Once again, to tell our compiler to pay attention to the directives, we need to turn them on. So the -ACC flag is the one we're going to use here instead of the -MP flag. Also, a very useful thing is to ask for some information from the compiler. How well could you do in paying attention to my directives? And so I strongly suggest that while you're developing codes, you also use this. It's optional. If you don't use it, the compiler's happy to go ahead and just do things, but it might be doing interesting things or ignoring your directives and you don't know it. So the -minfo flag, once again, is really useful. Only in this case, we wanted to tell us what it's doing with acceleration. And so this is useful. And when it's done, it will spit this a.out. Now, if you ask for info, it's nice and will tell you all of this stuff right here. In particular, it will tell you that it was able to generate Tesla code. And so this right here, it doesn't come out color coded like this, unfortunately, but this is what you want to look for. These are line numbers, by the way. So we had a directive on line number 9 saying, make a kernel out of this. And it tells us it was parallelizable. It was able to generate a kernel. And this is good because otherwise it will not, and it will not tell you. This is a big difference between OpenMP and OpenACC. It's maybe the main difference is that OpenACC, because it's a much newer standard, it was developed, 15 years after, 10 years, I guess, something like that, after OpenMP, had the luxury of saying compilers are smarter now. So if the compiler sees a data dependency, for example, it will ignore it. It'll tell you here that it's ignoring it, but it will just ignore it and spit out serial code. So your code won't speed up, but it'll be correct at least. That's very different from OpenMP. OpenMP was developed in an earlier era where it just said, if you put this directive in here, it's going to do it no matter what. So with OpenMP, we had to recognize a data dependency and not use a directive there. With OpenACC, we can be a little bit more blasé. We can just throw a kernel directive in front of a loop. And if there's a dependency there, the compiler sees, because they're pretty good at spotting it, it will instead ignore your directive. And it will tell you here in this output. It will down here say, loop has a dependency or something. And you'll know, oh, okay, it's ignoring my directive. So that is a big difference between OpenMP and OpenACC, is that OpenACC is a little bit smarter and will reject things that it knows are broken. And it will tell you right here. Otherwise, if you don't ask for -m info, it'll ignore it because it knows your directive is going to break something, and your code just won't speed up, and you'll wonder why. Well, this is a nice way easy way to find out. Okay, let me see. We've got some questions here. Let's see. What about private variables? Well, there are cases where we need private variables here. We'll get to that later on, but OpenACC is going to take responsibility in a lot of cases for moving things around and worrying about it. So kernels will do some smart things for us. We'll see that. We'll get to the differences as we go through. If there are multiple non-nested do loops, will they be parallelized? Yes, inside of the kernels, whatever block of code you have the kernels applying to, it'll take all the loops in there and parallelize them. So as per that earlier example. So it can bite off a number of loops at once. Is there some advantage using C over Fortran with OpenACC or Fortran over C, C++? No, there's really no advantage. They both work very, very well with OpenACC and with OpenMP, and we'll find out later on with MPI. So C and Fortran, whichever one subscribes to your own preferences. A lot of people, Fortran has fantastic array manipulation, and C has the world's worst array manipulation. So that's one reason people will use Fortran. On the other hand, C has a much cleaner code set. Fortran is carrying around baggage from Fortran 77. So you can write some awful code in Fortran if you want. And so some people prefer C for that, for keeping the code base cleaner. And so those are your own separate decisions to make. Whichever way you go, they're going to work fine with all the things that we're learning this week. Saxby example, should you restrict other variables? No. So for Saxby, no, we don't have to restrict any other variables. You can, and by the way, this is why I say people underuse restrict. Just throw restrict around. It never hurts unless you are one of those weird cases where you got arrays overlapping, in which case you should be very well aware of that, right? But it never hurts to overuse restrict if things aren't overlapping. It doesn't hurt and it only helps. So in our case, the only one we needed was for that Y variable, and then a compiler can be sure nothing's overlapping enough to break its vectorization type of approach. But if we applied it to X there or something, it wouldn't hurt either. Okay. Then it's because X isn't written to. Yes, as somebody else commented here. Tesla code. Oh, yes, I should point that out. So generations of GPUs come and go really quickly, and NVIDIA calls them by Tesla and Volta and Ampere, famous physicists mostly, I guess, scientists. And Tesla, so Tesla code is the term that's been hanging around for the last couple of generations of cards. So this is saying it's generating Tesla compatible code. So, and even though we're using this on Voltas and this also shows up with the Ampere code generation. So Tesla is a generation of GPUs. So that's what it's saying here. So that is I guess that isn't self-obvious. We work with the term so much. Let's see. Can race conditions cause problems if we have multiple loops? Absolutely. And we'll see how that gets taken care of. Kernels is smart. Again, these compilers are smarter when they're in their OpenACC mode than they could be with OpenMP. So kernels will not introduce race conditions. It'll accommodate those, but it can sometimes be really slow because it's paranoid about that stuff as well. We'll get into that, but yes, there could be race conditions, but kernels will never create them. But we'll talk about that. So these other things that are going on, somebody asked, what is vector, blah, blah, blah down here. These other things are more advanced. We're going to find out we don't need to know what any of this stuff is, but we're also in the advanced talk today going to cover it. So we'll get into this so that you do know what it is, but you're going to find out you can get very, very far with OpenACC and do a lot of great work without us ever having to pry into the details of what the GPU is. And this is, as my next couple slides will show, is very, very different than CUDA. So again, we'll get to this. I'm not going to talk about it just yet because we will cover it, but you don't have to. We're not going to need it to get some great results. And this is, as I just said, very different from CUDA. With CUDA, it's so closely tied to the hardware that here's the Saxby, just the subroutine. It's not the full code. Here's the Saxby subroutine in CUDA. And in CUDA, first of all, if you look at this, you'll notice that it's not even real C code. There's some stuff here that a C compiler just would not be happy about, like down here. So it's not even standard C. But more importantly, I think, is the fact that We got some mysterious numbers showing up in here, 31 and 32. Like, where did these come from? Our SAXP loop didn't have any of this. This is showing you kind of the hardware bleeding up, into our code. And it's because CUDA is very low level stuff. And, and this is, we're having to tie it to the hardware for some reason, even though it's a simple loop here. OpenACC is very, very different from that. And we're going to find that we can get so far today without even talking about what's inside of a GPU. And fear not, we're going to come back and we're going to talk about it, but we're going to get very far, get great results, get good performance on our codes without ever having to look into the actual architecture of a GPU. We're going to come back to it because, how could you possibly not discuss it? But we're going to find out we can use OpenACC without having to worry about the architecture or the details at all. Very, very different from CUDA. If we were doing CUDA course right here, we would start out having to talk about the hardware, particulars of the hardware. Before we do anything else, we'd have to talk about the SMs and how it spread things around and blah, 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 before we could even start to write a line of code. We're gonna parallelize our Laplace code here today and get great results without us ever having to look into the GPU at all and talk about its thousands of cores, right? GPU has thousands of cores in it. That's amazing, right? How can you have that many cores and blah, blah, blah. We'll get to it, but we're not gonna have to get to it before we get good results. So here's the Fortran CUDA version of just a subroutine. And just like the C version, it's got these hardware kind of dependent numbers stuck in here, and it's got a lot going. It's not standard Fortran either. That's why we're glad we don't have to use CUDA here. Again, here's the SAXP. Here's the whole code with SAXP. We stuck this kernels directive in front of it, and that's it. Now we've got a GPU code. And it's a big, big difference. So we don't have to change the structure of the code. We didn't have to make a new non-CUDA version, right? Your friends that wrote the original code here aren't upset with you. You didn't mess up the code, right? You've still, you still got the original code here. You just added in this one funny looking comment as far as they're concerned. So this is a huge win. Now, it looks too easy here with this kernels thing. We just, once again, like with OpenMP yesterday, why don't we just throw parallel for in front of every loop? Or better yet, why don't we just have a parallel flag? Somebody mentioned yesterday, where's the parallelizing compiler, right? Why doesn't the compiler just throw kernel in front of every loop and do it for me? And once again, the answer is because we need some human level intelligence to deal with a couple of things. Data dependencies and loops. Does that sound familiar? Because it's the exact same thing as yesterday. And a new thing here, we didn't deal with yesterday, data movement. What is that about? Well, we will get to there. And this is where you as a human being have to decide where directives are appropriate or not. And that's why we can't just throw kernels in front of every loop. Now, data dependencies, we covered yesterday. So everybody, I hope, is comfortable with the idea right now that this loop has data dependency in it. If we try to spread this loop out amongst the thousands of cores in a GPU, one core is going to be waiting for another core to deliver its results. And this is the problem. Now, the nicer thing about OpenACC is if we put an OpenACC directive in front of this, it will just say, can't parallelize this. If you look at if you run it, it won't speed up, and you go, why didn't it speed up? Because it would recognize you did something that was dangerous and invalid. And if you use that info flag and you look at it, it will tell you there's a dependency here. So I couldn't honor your kernel directive. So that is nice. With OpenMP, we know if we do a parallel for in front of this, it's going to go ahead and parallelize it, and then we're going to end up with some bogus results. But with OpenACC, it'll just refuse to do it. But again, it'll quietly do it unless you ask it for that information. So as you're working on the exercises today, if you don't use that at -m info, you might wonder why aren't my current directives having an effect? And the reason is the compiler saying you did something dumb, and I'm not going to let you do it. So, but we've been through this, so we don't have to go back through dependencies here. This is where I say it. So here's an example where I try to do a kernels on line 11 here, and it said, hey, you got a dependency, so I'm not going to do it. And the number one way you notice this is that magic thing that said, parallel Tesla code generated. That's not going to happen. Instead, you get this. So let's once again attack a code that we looked at yesterday, our Laplace solver. Let me see. I see some questions scrolling by here. Let's see. Are OpenACC directives only valid for GPU, not CPU? No, OpenACC will work with multi-core CPUs as well. We'll come back to this in the comparison talk at the end of the day with OpenMP and OpenACC. So you could use OpenACC to do a lot of what we did yesterday. Should you? Well, that's what we'll talk about at the end of the day. So the short version is, no, the reason that we're doing the topics that we're doing this week and applying them to the areas we're applying them this week is at the end of the day, it's where it does work. And the answer is, the short answer, but we'll cover it in more detail, is OpenMP works great. with CPUs, and it's the standard effective functional way to do it. And OpenACC works great with GPUs. And it's a standard functional effective way to do it. And although on paper, the specifications and the people that are cheerleaders for these things will tell you you should use them everywhere, it doesn't work out that way. But again, we'll circle back to that in more detail at the end of the day. Code be compiled to use OpenACC kernel with GPU is present at runtime, use OpenACC parallelization if not. Yes, as a matter of fact, that will automatically happen. If you make, if we do a code here and use these GPU directives and you run it on a device that doesn't have a GPU, it'll fall back and it'll run the CPU version of it by default. So again, it has the benefit of being pretty smart from the compilation perspective. Let's see. Source code is here, Fortran provided under the examples directory. It is not for the simple like SAXP, no, because it's just a couple lines of code. So I don't think I left that in the examples. So I could be wrong, but I don't think I put it there. But the source code for all those serious exercises we do, yes, you'll find there in the exercises or examples directories. Okay, and in particular, the Laplace solver, well, we have that sitting around already because we've been working on it. And once again, we're going to do Laplace, and we're going to do a head-to-head comparison with OpenMP. You're going to, and you've already got a head start on it because we do understand the code. So I'm not going to go through a detailed explanation of this code again because we did that yesterday. So I hope everybody gets the idea of how the serial code works. It's the exact same serial code doing the exact same algorithm. And once again, with OpenACC, we have the luxury of focusing on the guts of the code right here, the yellow part, because this is where all the action happens. So we get to apply our directives just to this part of the code, and we can ignore the rest of the code. And it's exactly the same thing with the Fortran version. It's the same starting code as yesterday. It's the same guts of the Fortran code that we're going to focus on. And we're going to go ahead and see if we can do something useful with OpenACC. Now, I sure haven't given you a whole lot of things to use in OpenACC, have I? So you don't have a whole lot of options here. And that's fine, because we're going to find out that we don't need much more than what we've got already to get some great results in an awful lot of cases. So you've got in the OpenACC directory now, which is where we're working. So even though the Laplace thing's sitting around your OpenMP directory, go to your OpenACC directory instead, because that's where the solutions for OpenACC and whatnot are. So go to your OpenACC directory under exercises. You'll find a Laplace code to start with there. Once again, to compile, it's the same as we were doing yesterday, except instead of compiling for OpenMP directives, we want to compile for OpenACC directives. And by the way, in case you wonder, they can both live in the code at the same time. You can use both of them together. You could start with the code yesterday that has OpenMP directives in it if you want. I would suggest not doing that to save yourself some confusion. But they're perfectly happy to work well together. And we'll get onto that talk with hybrid computing and later on. But at any rate, I would suggest you start with the serial Laplace code like yesterday. Add in the directives that you've got available to you, compile like this, you'll get an A.out, go ahead and run it and see what's up. Once again, I highly suggest you use the -info flag while you're doing this so that you can make sure your directives are actually doing something, and you can ignore all the rest of this stuff. Before the end of the day, it'll make sense to you, but we'll find out we don't really need to know it to do a lot. Now, there's one difference with the way we're going to run today, and that is that we don't have hundreds of GPUs, but we got hundreds of you. So in order to accommodate everybody, we're going to have to use the batch system today. Now, I know yesterday I said this is not a workshop on supercomputing, in high performance computing environments, so we're going to shield you from having to learn anything about the batch system. Well, we're going to do that. I'm going to give you a little batch job that will run things for you, but we do have to use the batch system because we can't have everybody just sitting on top of the GPUs. We just don't have enough GPUs to share with ourselves and all the other research going on in the machine. There are thousands of projects running on bridges right now. So you will have to use a simple little batch job, but I've already written it for you. You don't even have to look into it. You don't have to understand anything about it, but this is the way we're going to run our GPU codes today, is that after you've written your A.out, you type sbatch gpu.job, and that gpu.job batch file that's sitting there will go ahead and run the job for you. And what it will do is it will go ahead, it will run on the machine, hopefully pretty quickly, and you will get back from the machine, from the queuing system, an output file. It'll look something like this. The number will differ, and it'll come back and you'll get the output file, and that will have all of your output in it. And you can see your timing from that. So it's a pretty straightforward process. And if you want to really see what's going on, if you want to dip a little bit further in the queuing system, if you type SQ, you can see your jobs and see where it is. So there's you could dig into it. And knowing a queuing system is not a bad thing, by the way, if you're going to work in a large, serious shared environment. queuing systems are very powerful and can do lots of wonderful things. They can email you when your job is done running that took 2 weeks to run, and they can start other jobs that are done, and you can run thousands of jobs if you're doing parameter searches. So queuing system's great, but I promise you we wouldn't talk about queuing systems this week. So this is as much as we'll have to use. So I hope that makes sense to you. So here's our exercise, and we're not going to take a lot of time for it for reasons that will make sense after the exercise is done. But we're going to give you 20 minutes to get a speed up with the directives that we have so far, which is pretty much the kernel's directive. So go ahead and edit the serial code, stick in the directives where you think they might be useful, compile them, and then run your a.out file by typing sbatch gpu.job. It'll grab your a.out, it'll run it, it'll take care of running it for 4,000 iterations, so to run it to completion, and you'll get an output file back that you can look at for your timing. So let's go ahead and get to work on this. We'll give ourselves till about half past the hour, maybe a little bit more. And that's not a lot of time again, so but there's a reason for that, because we're gonna need some more steps after we do this to get interesting results. So go ahead, I'm gonna answer questions. Those of you that want to work on the exercise can, as per usual, completely tune me out while I pick off these questions. Okay. Something covered. Do we have to request the GPUs like GPU? Well, like we just covered that. The batch job will take care of that for you. Feel free to take a look inside the batch job if you want to see what it's asking for. It's very, very straightforward. They're not complicated. We force it to run on CPU with OpenACC. Basically, for most people, you want to run on a GPU if it's there, and if you don't have a GPU, it'll run on a CPU by default. And for most of the people that really would care, you could just compile it without the GPU, -ACC, and then it'll be only the serial version, or you could switch to the MP for the parallel version. But we'll see. There's a multi-core. There's ways you can select devices and whatnot. We'll get into the advanced talk if you really wanted to be fancy and at runtime decide not to use a GPU that's there or something like that. So it's there, but it's most people wouldn't choose to jump through the hoops that way. We'll use OpenMP to divide up jobs, then be divided up using OpenACC for GPU. Well, you can mix and match them if that's what so you can use OpenMP and you can have multiple threads, each accessing a GPU. As a matter of fact, that's not uncommon. I just helped somebody with that last week, as a matter of fact. So it's possible to do, if you've got a machine and it's got a CPU with a lot of cores in it, you want to use those, and then the cores can talk to the GPUs independently and break the workup. It's absolutely possible to do that and mix and match them. And by the time we're done here today, I think it should be clear how to do that. It's that type of hybrid computing. Do we need to set an environment variable for how many GPUs to use, similar to num GPUs? No, we do not. There are environment variables to allow you to manipulate that stuff, and we'll briefly mention them in the advanced stuff, but by default, you'll be fine. It'll grab the GPU that's at hand in the sbatch command. Yeah, if you're using, good point there. Somebody pointed out if you use SQ, you might want to use -U to just look at your own jobs instead of everybody else's in the queue. That's probably what most of you want to do. How do we make a reasonable comparison between the accelerated version and the serial version, since one of them is using the CPU? Well, at the end of the day, all you care about is how much faster you're running. So you're just going to say, hey, the serial version is using the CPU. How much faster does it run when we bring in the GPU? I think that's the comparison that you probably use to determine whether you're successful and wasting your time or not. It's just CPU versus GPU. As a matter of fact, to be really fair, you want to compare the CPU with a really good OpenMP implementation, right, to the GPU, because you want to make sure you're using a CPU to its fullest. That's what we'll do. We'll compare the best CPU version to the GPU and see if it's worth, see if our GPU is really pulling its weight. There are reductions, and they might be necessary, but the nice thing about kernels is it worries about that stuff for you. So it's like I say, it's a smarter level of directive. And so kernels will take care of reductions for you. And you'll find that out with our example right now. There still is reduction because you might want to take charge of those things. We'll look at that in advanced OpenACC stuff. But kernels is perfectly happy to worry about things like reduction, which is pretty nifty. The module should be loaded for you automatically if you've got the bash RC file from your exercises thing yesterday. And if you don't, go back and look at those setup slides. You want to run the ~training/setup command, and that will automatically load the module for you when you start up. The AC directive inside the while loop, does that mean temperature matrix will be sending to from the GPU every iteration? Yes, it does. The slurm output will come back. It will automatically send back to your directory, your home directory, or for any directory that you submitted the job from. The slurm file will just magically appear there. So when it's done running, give it a minute, or you can look at SQ and see if your job's still running, and the file will just magically appear from wherever you typed SBatch from. The way you have assembly language for CPU, what is used for GPU? Well, it's actually PTX code at a lower level that CUDA gets translated into it, but nobody ever works at that level, and be glad you don't. So there is a lower level assembly language, but as I was saying, GPUs change from one generation and one vendor completely to the next. So trying to track of that stuff is very difficult. For example, if you use machine language with CPUs, life has evolved, but incrementally and slowly since the 8086 back in the 70s. They just kept growing the instruction set in the Intel world, which is a large number of chips. And even if you go to, say, a power chip or an ARM chip, they're kind of similar instructions. That's not true in GPU land at all. The GPU hardware has changed and morphed so much and so rapidly that the instructions from one generation, even with the same vendor, to the next, change a whole lot. So you do not want to be working at lower levels if you can avoid it. Whereas, like I said, some assembly code from the 90s, doesn't look drastically different from assembly code today for a lot of applications. The extension, every year they just extend it. The difference might be these days you have more vector instructions, but that's not true for GPUs. So at the low level, it's very, very ugly. Do we need includes? No, we don't need includes. One of the benefits of directives is you don't need to include. The compiler's taking care of all of that stuff for you. So it's not like a library where we have to bring in include statements and worry about what to link. We don't have to do any of that. Same with OpenMP. So the question again, if ACC directive is inside the while loop, does that mean the temperature matrix will be sent to and from the GPU for every iteration? Yes, it does. It will be sent back and forth. You're a little bit ahead of me. We will discuss that, the details of that in a couple of slides. Should we launch the batch job from a login node or from a compute node? From the login node. We don't need to be on the compute nodes because we're not computing on them. We're computing on the GPU. So we're doing everything from the login node. Will work just fine. Unknown option -ACC. That's odd. I will guess, if I had to guess, because there's no reason you should see that. Are you sure you've got the right dash? If you're cutting and pasting stuff, there is in the world of character sets, there is a short dash and a long dash. Like one's like a minus sign and one's a full dash. And if you're cutting and pasting from PDF files, they get switched and causes problems. So make sure you're using the regular dash like you use for all the other options on the keyboard. Uh-oh, you answered your own question. Okay. Let's see. Do we need to add private? No, we do not. Kernels are really, really smart about all this stuff. They will figure out what indices are where and everything else. So the error, unable to open gpu.job. If you don't have a gpu.job sitting around in your directory, we can type ls. If you don't see a gpu.job, you're in the wrong directory. Maybe you're sitting in the OpenMP one from before. So make sure you're getting to the right exercises, OpenACC directory, and you should see a gpu.job sitting there. Again, everybody's ahead of me answering these questions. I'm doing the best I can to catch up. Let's see. That ugly compilation error terminated by signal 11. Let's see. Assuming you've got the right module loaded, you did our, you've got everything set up correctly. You're using our setup script, which is the main thing. So I hope you did go through our setup process. You're using the right module. You're not using your own guess at a module or something like that. Then no syntax error or anything should look like that, but try running the compilation on just our generic serial code and see if that works. And if that works and this error is showing up when you try it on your edited version of code, then the compiler is just being very, very unfriendly about some kind of syntax error or something that you're generating. But I'll guess it's the wrong module. Let's see. As I said, somebody asked a question earlier, we don't need to worry about making anything private here. Don't need to compute. No. Asking about the restrict keyword, it never hurts to use it unless you're actually doing some weird thing where you're overlapping data structures. So I won't discourage anybody that wants to use the restrict keyword. Throw it wherever you want. It won't hurt. It can only help, except for those odd exceptions. Can we manage memory using OpenACC? Absolutely. We will get on to that very, very shortly. So we'll talk about that in great detail. Yeah, don't worry about your performance results so much just yet. That's why we're not spending a lot of time on this exercise.
John, I would like to caution people one more time of direct messages, because the chat scrolls by so quickly. If you direct message, sometimes I might not see it or you might not see it. Better to put it in the entire chat for everyone.
Yeah, so a lot of you are doing some astute analysis on why you're not getting great performance here, and I will say you're not wrong. So that's why we're not beating our heads on this wall for more than another, say, 5 minutes or so, and then we're done with this exercise. And yeah, we don't need to specify a reduction. There is a reduction going on here, right? And you'll find that kernels, if you look at that -minfo flag, you'll see that kernels was actually able to do a reduction for you. So it's one of the things that you'll see there. If you go scroll to it, you'll see, oh, it found out there was a reduction going on and created one for me. So kernels is a whole level of smarts beyond what was available when the OpenMP spec was being created. But reductions are allowed in OpenACC, just not on kernels because it's responsible for it there. We'll get to that later. You don't run the slurm output file. You run the SBatch, and then the output file that comes back you can look at with your editor, or in Unix there's the more command, I think is what I suggest here. So you're not, that output file is what you look at for output. Actually, it's unfortunate that our a.outs are executables, and slurm calls its output files slurm whatever .out, but it's not an executable. It's just the output from the run. So you're not allowed to try to execute it. You're just allowed to look at it. No, you're fine. If you've got the thing compiling right now, you've got the right modules loaded. Don't worry so much about the run times yet. Well, the person that's using a reduction with the ACC parallel 4, you're a little bit ahead of us since you're using ACC parallel 4 loops, and that is where you would want to specify the reduction because you're now taking charge. You're of how to do the loops. Kernels, like I say, is taking a lot of responsibility. So we'll cover that. You're a little bit ahead of us there. What does the implicit copy mean? We're going to talk about that in the next couple of slides with our solution. Yeah, you can't run the output. The thing called slurm dash whatever dot out is the output file. It's just a bunch of text that's your results. So you're not allowed to run it. So that's good that the system doesn't let you, but you are allowed to edit it and look at it. So you shouldn't try running it. You should try either using your editor on it, or in Unix, there's a more command or a cat command that'll, let you expect text files. Okay, we'll give ourselves a couple more minutes and then we're going to go ahead and look at the solution. And if you're not getting great, spectacular results right now, fear not, you're not the only one. But do, make sure that you at least got the thing to compile. That's our goal here, is to put the kernels directive in, get it to compile and get some results. Make sure that process you can step through, but don't focus on the performance just yet. Yeah, that's right. In order to type the input in, because when the code runs, it asks you for how many iterations to run. We stuck that in the job file as well. So that's why if you look in the job file, if you care, you'll see that it pushes 4,000. It says run this thing 4,000 lines. It sticks that into the as the input into the code as it's running. Is there a way to differentiate between the serial slurm and the accelerated slurm? Well, there are flags. You can easily tell Slurm how to rename your job files as it comes back. So if you were a regular Slurm user, I'd tell you to do that, and then you can organize your files as they come back, etc. But in this case, to keep life simple for you, they come back with different numbers. So the numbers that they come back with reflect the job thing. And if you care when they come back after you've just done one that's interesting to you, you could just rename it right then. So by default, Slurm will just give you different numbers back. But for people that are actual real Slurm users, batch system users, they could easily, you could change it so it names your files to meaningful things when they come back, et cetera, et cetera. It's fancy, but we don't want to get into that here. Yep, if you got it to compile, you got it to run, you got output, that is indeed the win. That's all we're looking for at the moment. We're not going to worry about the performance because we're going to discuss that in just a second. How we change the number of processors? That's a good question, because so far I've said there are thousands of processors working away in your GPU out there, and I haven't really talked about exactly how many or how are we asking for them. So far, it's been hidden from us. We're not worrying about it. So we'll get into that, but it is interesting so far. We haven't had to worry about any of that. Your Slurm output files are written to in real time as it's running. So if it's empty for just a second, don't worry about it, because it's, it could be filling it up while it's right. Creates it when the job starts, and then it writes to it. And then when it's done, it's full. So if your job's still running, it could be briefly in an empty state, but it should write something back before it's done. Even if it writes back that, your code crashed or something, you'll get something back. Okay, with that, let us go ahead and look at a solution. And so many of you were observing you weren't getting spectacular speed ups, and that is actually to be expected. But here's the solution that probably most of you homed in on, something like this, because we only had one possible tool to work with here. It's kernels, right? And we have two loops where all the work is done. So this is where we'd throw kernels in front of, and we'd say, okay, turn these into GPU codes. And indeed, you look at the minfo flag and it tells you it could do that. It turned these into GPU code, generated Tesla code. And so this is the solution. Here's the Fortran version, exactly the same thing. And so this is pretty much where I expected many of you to end up. And the minfo flag should tell you in both cases that it was able to, where you had those kernels directives, generate some Tesla code. So far so good. Now, this is kind of, whoops. Where is that? Oh, here we go. This is kind of nifty in that you'll notice that down here, it was able to generate a reduction. Actually, kernels could look inside of that loop and say, hey, what you got going on here needs a reduction for this DT variable. And that's pretty smart stuff, right? It's actually able to recognize this as a private variable, you know, it's being written to, and by the way, it's also has a max operation, so it created a maximum. So this is the kind of thing with OpenMP we definitely had to, you know, do ourselves. Kernels is pretty smart. And again, it's, you know, OpenACC has the benefit of being a 15 years newer standard than OpenMP, so it's building upon, you know, the ability for it to assume it could be much smarter. So there's our reduction. Okay, and like I said, it was able to figure that out by looking at the code in here. So we could have, a couple of you were messing around here and said, okay, could I take control of this, or I'm trying to create a reduction myself? And you can take control. We didn't do it here, but OpenACC allows you to take over the loop and say, I'm going to be in charge of what's going on, and we could do something like that here. We didn't do it here. We relied on, I didn't even introduce the idea to you here. Instead, I said we're using kernels. Okay, well, let's look at our performance though, because that's the interesting part here. And our serial code runs in, you know, roughly 20 seconds. And most of you probably found out that your performance on the OpenACC code was somewhere over 30 seconds. So with all of our efforts thus far, we managed to slow our code down by, you know, a lot. So that's pretty terrible. It's even worse if we compare it to what we know that CPU can really do with what we did yesterday with OpenMP. We're way slower than the OpenMP code. So is the moral of the story that GPUs are terrible and OpenACC is useless? Well, not quite. Instead, we are now led on to the second thing that I said we as human beings have to worry about besides data dependencies. I said we have to worry about memory management. And so now we find out why we have to do that. And one way we can find out what's going on in our code is with a profiler. And as I said, profilers are wonderful tools. We're going to talk about some really serious, nice profilers at the end of the week, because I don't want to confuse us with tool options right now. We don't need them yet, but you'd be silly not to use them once you get seriously into doing this kind of coding. Fortunately for us, built into this compiler is a really nifty little mini profiler, which does do a pretty good job of telling us where our time went. And it is as simple as just turning on this environment variable. You don't even have to recompile. If you just set this environment variable right here and rerun your code, it will spit out this little profile right here. So you can do that if you want. I've done it here, and so we can pick apart. That's kind of nice. It's not as nice as the pie charts and bar graphs that you get out of a full-blown profiler, but works at the moment. So we'll settle for it. And when I run this profiler, it spits out all this information about my code. I can see in its breakdown here, it's telling me where it spent some time. And I can see on the execution side where it says it launched a kernel, I can see what it was doing. It said it launched this kernel 3,372 times. That sounds about right. And if I look at the total time spent, these are in microseconds here. So if I look at the total time spent, it's spent about 0.2 seconds there running that kernel and 0.3 seconds running the second kernel. And then there was a little reduction in there too. That took a little bit of time to accomplish the reduction. So if I look at the time it spent running, it's actually pretty good. It's pretty fast. It actually ran these kernels really quickly. So that sounds good. Well, where did all my time go then? Well, if I come over here and see these other things it's talking about data copy ins and data copy outs. And this is where all of my time is going, into these data copy things. Well, what are they about? Well, as I mentioned to you very briefly in the intro to parallel computing talk, GPUs, much as you think they're just plugging into the motherboard, I mean, really they're connecting through this PCI bus, or maybe even potentially a better version of PCI bus called NVLink, NVIDIA's proprietary bus for connecting GPUs, which might sound really fast because it's, PCI bus runs at 16 gigabytes a second, and or even faster with Gen 4. The NVLink's really fast. It's even faster. But at the end of the day, it's much slower than the speeds that CPUs connect to their regular memory with, or the GPUs connect to their memory with. Way slower than that. So you think that the PCI bus is fast because it can move some video frames for a video game back and forth. But compared to memory transfer speeds, memory access speeds to regular variables sitting in memory, it's very slow. And so this means that whenever our code has to move data to the GPU and back, it's going to take a relatively long time compared to its regular memory access speeds. And so, and GPUs, as a matter of fact, have very, very fast access to their main memory. These days, they're all well over a terabyte a second. One of the reasons GPUs are so great. But again, the data has to be sitting in this GPU memory first before you can take advantage of it. And in our case, what we're going to find out is that our Laplace code is moving this metal plate, this temperature and temperature last, back and forth over this PCI bus. And that indeed is where all this time is going right here. Our copy ins and copy outs. That's saying copying onto and copying off of the GPU. That's where all the time is going. So this situation right here in our particular code ends up turning into this. We've got this array that has to get jammed back and forth every time it goes into a kernels region. And so that is where all of our time is going, and we've got to fix that. That's the memory management issue that I'm talking about. Here's exactly what happens in our code. Every time in our while loop, we hit a kernels directive, the kernel says, I'm going to take responsibility. It's a great thing about kernels, right? It does all these smart things for us. It worries about reductions and whether things should be private or not. It does all this for us. But one of the things it does is it says what variables are needed on the GPU. And it looks at everything involved in here, temperature and temperature last, and says, I better copy those over to the GPU so that they're there when I need it. And when it's done, it says, what data did I compute on the GPU? Well, I messed with temperature and temperature last, so I best copy them back to the CPU in case it needs to access them. And so that's what it does on the first kernels region. It does the safe thing. It says, anytime I mess with data, I copy it on, copy it back. Comes down to the second kernels region, does the safe thing again. And so what we've done here by sticking in these kernels is we've created in our while loop a situation where 4 copies happen every iteration of the loop. And they are big copies. They're our main data structures. They're, actually they're relatively small by normal HPC standards. They're, 8 million elements, each one being 8 bytes a piece. So they're 8 megabytes a piece. But even with this relatively smallish problem, it's enough to add up and become a big issue. And this leads us on to the second thing that we need to deal with besides data dependencies as human beings. We need to worry about data management. When do things really need to move back and forth so that we can be smarter than the compiler, which is always paranoid? The compiler is always going to move things if there's any chance that they're needed. And we as human beings can look at things and say, maybe things can stick around and aren't needed or can be ditched. And this data management is where we come in. And data management are just more clauses that we have, directives that we have where we can control this. And the ones we're going to start with, there are a number of them. We'll get to them all before we're done, but the ones we're going to start with that'll be sufficient for our problem at hand will be the ones that say, we're going to take over in this region that our directives apply to. We're going to take over management for some particular list of variables that we give it. We're going to be in charge of moving the data back and forth. So kernels can do everything else except for these variables that we're taking charge of. And for these variables, we have a number of things that we can tell it to do. We can say, in this region, we're going to copy at the beginning of the region where our data directive applies, copy this data in, and at the end of this region, copy it back out. And inside of this region, don't ever move it. We're in charge. We copy it onto the GPU at the beginning, copy it off the GPU at the end, but you are not allowed to move it outside of that. So if there's kernels inside of this region, they don't get to do anything with these variables that we're taking over. And so you can think of this as like the GPU is running subroutines, and subroutines have input variables and output variables. And the copy command is going to be for something that's both an input and an output variable to the GPU. Sometimes, however, when you've got subroutines, you only have input variables. You have things that go into the calculation, but you don't need them to be copied back. You don't want to waste that time. So copy in says, hey, for this thing at the beginning of the region, copy it onto the GPU, but then when we're done, just abandon it there. I don't need it to be copied back. Don't waste the time because it's not an output result. Likewise, sometimes things are only results. You only need them to be copied back out of a subroutine. You don't need them to be copied in. There's something that's calculated within a routine. So that's what copy out does. It says, don't waste your time at the beginning of the region or within the region ever copying onto the GPU. But when you're done, copy this back off of the GPU. And the last one here is also quite common, which is create, which basically says this is a temporary variable. This is something that's used in the middle of our calculation. It's like if you have a subroutine again in your code and you call it, you might use variables within that subroutine, but you don't need it to be copied into the subroutine or copied back out. They're just used inside of it. And it says, okay, this is something the GPU can use in the calculation, but don't waste your time copying it onto or off of the GPU. So these data clauses here give us the ability to manipulate data. Matter of fact, we can even do it at a finer grain using array shaping, which says sometimes you don't even want to copy the whole array onto or off of the device. You just want to copy some section of it. And so this is where array shaping comes in. And array shaping and slicing for Fortran people, you use this stuff all the time. You know, it's just the way the array stuff set up for C people. It's pretty easy to understand. It basically says instead of copying the whole array A, just copy in some subsection of the array from 0 to size. Instead of copying the whole array B, just copy in this section of the array. This has got 2 dimensions to it. Just copy in this part. Oh, that's 1 dimension. Just copy in this section of it here. So, no, it is 2 dimensions. So these array shaping and slicing things are is 1 dimension here. I'm being dumb. It are standard ways to say I don't need to copy the entire structure in. I just need to copy some slice of it. There's a little bit of a difference here in that Fortran uses start end because that's the way it always operates with all of its array slicing and shaping just as part of the language standard. C, instead, people are more comfortable with start and then the length of it. So that's a little bit of difference in the way they're specified here. It's confused me up here. So start and length versus start and end. And we can use this anywhere we have a data clause if we don't want to send the whole array. So that's how these things work. Let me see. I see some questions flying by. Let me see where we got it. Some of you or somebody's already using data copies up there. Okay, you got ahead of us on the exercise, I assume. Let's see. So looks like I misspelled a parameter or 2 dashes. Let's see. So the way to truly optimize is load the GPU memory and then run a comment. Well, we'll talk about that in just a second. Yeah, that's pretty much it. Let's see. So if you don't include data clauses, the kernels will by default do what it thinks is the safest and simplest thing. Sometimes kernels, so that answers the last questions there and leads me right onto this slide here. Sometimes kernels can do slightly smarter things, but only if it's very, very sure. So kernels tries to be as smart as it can be, but it's very paranoid. It's going to make sure the data is always there if it's needed, or it is always moved back if it could possibly be needed afterwards. So it will try to be smart. Here's where it's kind of trying to be a little bit smart here. And we can see this with the dash info flag. It'll tell us what it was able to, where it was generating copies. So if we put kernels in front of this, for example, we can see that it was kind of smart here with array B. It looked at array B and said it needed to make a copy because array B, so we got 3 arrays here that we're setting up before we come into this loop here. So array B has to be copied into this loop because it's using values from B that are brought into the loop. And it's copied out when it's done because it could be used somewhere down here. But if we look at array C, it was actually a little smarter. It could recognize that array C, there was no point in copying array C into this because C is completely initialized by values that are brought in by A and B. There's no point in copying C in here, right? C is completely set within the loop. What would be a waste of time? It's kind of smart. It could recognize that. And with array A, it was able to recognize even smarter that array A was completely set up within a loop by just some calculations going on here. No point in copying A in here either. So kernels is sometimes able to do some smart things and minimize some extra data copies, but it's always going to be paranoid. Your ability to see the bigger picture is important here. So that's why data clauses are important, because as humans, we can help kernels a lot. Now, data regions do have some consequences. You can't just take over responsibility for copying these things and assume that nothing is going to happen bad. If you start managing the data, you do have to pay a little bit of attention. Now, I'm going to give you an example here of something stupid just to kind of highlight it. It's an easy way to see here we're taking over the data management and doing something dumb. Don't use this as a reason to think, oh, data management's really tricky. I'm just using it to show you how we can do dumb things with data management. Data management is pretty much you using your common sense. When does the data need to be there or not to help out the compiler? But let's look at a case here where we've got a kernel running on the GPU that just takes an array and sets it equal to 1. So we got an array, it's initialized to randomness, and it gets set equal to 1. And when we're done, we print out one of the values for the array that we set equal explicitly to 2. So we set array element, the whole array set equal to 1, and then array element 10 is set equal to 2. And when we're done, we print out element 10, and it's 2, right? That's exactly what we'd expect. The rest of the array is 1, and this value is 2. Great. Now, let's take over, well, if we look here at exactly what's happening. When this runs, kernels will copy the whole array thing onto the GPU. And when it's done, it will copy it all back to the host. By the way, the terms that are used in the documents for GPU and CPU are device and host. So I'll mix them in a little bit here just so you're comfortable with it. So again, the specifications don't call things CPUs and GPUs, they call them devices and hosts. So this gets copied onto the GPU and this gets copied back to the host or the CPU. At the end, this gets set on the CPU, and when we print out the result, it's 2. It's exactly what we'd expect, right? Nothing really profound running here. But let's say that we take over the data management for A here. So we decided we're going to be in charge of A, and we put this data copy of A around this region here. This means we are telling the compiler, you will copy A onto the GPU right here, and you will copy A back off of the GPU right here. And in between here, I'm in charge of A. You are not allowed to move it. That's what the data regions do. So if we run this code right now, what we'll find is that when it prints out element 10, it's equal to 1, not 2, even though we set it equal to 2 here. So what exactly is going on? What's going on is at the beginning of the region, it copies A to the GPU. Then this right here is running on the CPU. This ran on the GPU and set the whole array equal to 1. This ran right here on the CPU. It's not in a kernels region. It's just some normal CPU code. It ran on the CPU and set array element 10 equal to 2. But then at the end of the data region, this got copied back from the GPU onto the CPU and overwrote the element A, the array A. So it kind of overwrote this change that we made here, so that now element 10 is equal to 1. So I hope everybody can see what's going on here. It's dumb. It's not the kind of thing you run across all the time. We kind of introduced a problem here, but I hope you can see that when we take over this data management, we're really in charge. We're overriding what's going on, and that we need to be aware of when the data is on the GPU and when we're writing it back to the CPU, because we can't overwrite things. We need to make sure the data is in the right place at the right time. So let me see, got some questions here. We use data copy in A where we have A equal to 2.0. So if we used copy in, it would copy A on here and it would never copy it back. And then this would still be okay, but then we'd never have the rest of the array A equal 1 would never get copied back to the CPU. So if we use copy in here, so the question is what would happen if we use copy in? So if we use copy in, it will copy the array on here. It will set the array equal to 1, but that will never have an effect. It will never make its way back to the CPU because there's no copy out if we just use copy in. And so what we have here is this element would actually now be equal to 2 because it would never be overwritten. So this would print A equals 2. But if we looked at the rest of the array, it would never be set equal to 1. So that would be the effect there. Okay. So, I mean, one way you'll hear this described is we've got the compute region and we've got the data region here, and we got to, you know, make sure we're aware of which one's which. But in reality, like I said, don't overthink this. Just do be aware that when you introduce data regions, you could break the code if you just do silly things. So you need to be aware of when you're moving the data, and what the idea is, you can do a better job than the compiler's super paranoid way. So in general, you'd like to have in the perfect world, all the data sit on the GPU, excuse me, as much as possible. The GPU is, you know, faster than the CPU, you hope. It's the whole reason we're using it. You want the simulation to sit on the GPU as much as possible. Now we're going to find out that we can also control data point by point, line by line, instead of data regions. As a matter of fact, I'll introduce now the one that we might find useful for our next exercise, which is update, which allows us to control this line by line. So we don't just have to do it with regions. We can also do it line by line. We can say, move this onto the GPU right now, move it back from the GPU. And the update clause will allow us to do that. So we can say we either want to update the host or the device. So if we say we update the host, this will say grab from the GPU, grab this variable and move it back to the host right now. And only once. It's not a region of code, it'll just do it right now. So we can control point by point things as well. And we'll also introduce, there's another couple of variations on this I'll introduce afterwards, but these data movement things will be more than enough for our exercises right now. Control it by region, or also to control it line by line. So now we're on to our real exercise 2, which is to go ahead and fix the performance here of this code. We've got something that runs correctly, but it's terrible performance, and we know why the performance is terrible, because it's thrashing, moving this memory back and forth. So can we as human beings fix this with these data directives? And so you've got the directives now, you've got the kernels directive. So you can start with your exercise 1 solution if you got the kernels directives in there, or my solution, which I call Laplace_bad ACC, means it's got the kernels directive, but it's got bad performance. So start wherever you want and add in these data directives. And again, ask yourself as a human being, you know, when does the data have to move? And in the ideal world, the data just sits on the GPU the whole time. But you can't always do that for a couple of reasons. The most common one of which is the GPU memory isn't usually as large as the CPU. Most GPUs have memory sizes of 16 or 32 or 40 some gigabytes. And the reason for that is that the fast GPU memory is expensive and tight and closely coupled, whereas your CPU has all this RAM chips just piled in there. And so CPUs these days have hundreds of gigabytes or terabytes of RAM, like on Bridges nodes. So a lot of times the problem is too big to fit on the GPU all at once. So we need to move things piecemeal onto and off the GPU. That's one reason we can't just say, oh, just put the whole thing on the GPU. The other thing is, as we're finding out, and as we'll find out more as we go through this, GPUs aren't as smart as CPUs. They're not as flexible. So sometimes things have to be done on the CPU. A trivial version of that is I/O. I/O, the input and output, has to be done on the CPU. But there are other things too that the CPU can do that the GPU can't. I keep saying the GPU's got thousands of cores. We haven't looked at exactly what those cores look like just yet, but it might give you a clue. They're a little bit simpler than the CPU cores. It's not that NVIDIA is just light years ahead of Intel, for example. It's that the cores are simple. So some things have to be done with CPU. So there's a reason we can't just put the whole problem on the GPU always, every time, but that's the ideal. You'd like the whole problem to live on the GPU the whole time if possible and minimize those data transfers. So let's see how close you can get to that with the data directives we have right here. So that's our exercise. And we are coming up on our break, and I don't intend for people to use the break as the exercise time. So you can if you'd like to. It's good that it works out this way, but if you, I'm not planning on it. So when we come back from the break at the top of the hour, we're on our break in 5 minutes. So those of you that want to disappear, we'll come back to the break at the top of the hour, and we will start then with another about 35 minutes of exercise time. So feel free to take a real break if you've scheduled it, and we'll start exercise time at the top of the next hour, and we'll have Q&A and everything else. And by the way, I may disappear. I will disappear over this real lunch break, and once again, reboot the machine in the interest of keeping Zoom stable. So if you ask questions over this upcoming lunch break, I will never see them in the Zoom chat because it doesn't keep a history when I bring it back up. So when you see me disappear, please don't ask chat questions to me, or I'll never know that you asked them. Wait till you see me come back up in Zoom. But anyway, let's start this exercise. I'm going to answer questions right now, and you can tune me out for as long as you like. So let me see what pending questions we have here. And the reason why that element 10 equals 2.0 ran on the host and not GPU, it's outside of the kernel. Things in the kernel run on the GPU, things outside the kernel run on the CPU. It is indeed that simple. If you're using 3 variables in the kernel, can you manage only one of them and expect the rest to be auto-managed? Absolutely. They will be auto-managed. If you don't take them over with a data directive, kernels thinks it's its job to manage it. So if you don't manage them, kernels will. And kernels will never do the wrong thing in terms of correctness, but its paranoid insistence on correctness might make it do something that's inefficient. The kernels is happy to manage everything for you, in which case its answer is going to be, unless I'm absolutely positive, I'm copying in and copying out. And by the way, that's why for scalar variables, again, meaning not vector or array variables, usually you're happy to let kernels do that because it'll do the paranoid thing. It'll copy all of them on and off, but who cares with a scalar variable if it gets copied onto and off of? That's fine. Single individual variables, if they go back and forth all the time, nobody cares. They take no time. It's only the big arrays that you really want to be careful about. Does the export need to be before the compile? No, that's the neat thing. That thing works at runtime, so you don't need to worry about it compile. Oh yeah, but the info does come back in a Slurm file. All the outputs going into your output file. That's where it's running. These videos, we are discussing how we can more quickly get these videos posted. Instead of going through the full editing process that we really prefer for quality reasons, we might do an abbreviated editing process and get these up very quickly. We were just discussing that this morning. So we'll have an answer by the end of today. We may have a very quick turnaround time on these videos, quicker than we prefer. They'll be a little bit cruder, but they will be up. So that question is in the air. With OpenACC, do we need to manage reductions directly? Not with kernels, you don't, but we're going to see that once again, just like with OpenMP, you might, for reasons of performance or flexibility, want to take responsibility for that. And that's where you will have to worry about reductions if you want to do that. And it shouldn't be that intimidating to you as an OpenMP programmer, but when we get on to the using OpenACC parallel loops directly instead of kernels, you would have to worry about the reductions there. So you want to make sure that you're looking at the output from the batch file. Actually, you know what? Now that I think about it, maybe we need to put the export in the batch file to make that happen. Yeah. Oh, somebody just answered. Yeah, that's right. So yeah, you need to put that in that batch file. You need to edit that into the batch file because that's when it's running. So if you edit that into your batch file, then it'll spit it out when it runs. Otherwise, it's not there. I didn't assume everybody would want to use that profiler, but feel free. So, but you do need to add it into the batch file. And by the way, the reason I assume people didn't want to use a profiler is the simple timing. Believe me, when you do the right thing here, the timings, the simple time that comes back is dramatic enough. You won't need to be peering at the profiler to see if you're doing things. You'll just see your times will improve drastically if you start minimizing unnecessary transfers. So you don't need the profiler to do this exercise, but I totally respect if you want to see what's up with the profiler. That makes sense too. In which case, yeah, include that export inside of the edited into the batch job. Does the Pragma use all of the cores as much as possible by default? Yes, it does. It's trying to do all the smart things. Again, it's kind of a higher level of smarts than in OpenMP, so it will try to use all of the available cores to do all of the work as best as possible. So you don't, that's why we haven't been worrying about it so far. We haven't had to manage any of that. And you'll find that will get us pretty far. And the advanced stuff we'll talk about later today, we'll start talking about how the cores are actually distributed and how work is broken up and how you can affect that. But we'll find we can get very, very far without us having to even know how many cores there are, which we don't at this point. If you have so the person is having a problem getting code to run at PSC, the thing to do, and you shouldn't have had to wait to this workshop to do it, is submit a ticket. We're happy to help you. That's what we do here all the time. So send in a ticket with some details and you will get, we're very responsive. It's not, our ticketing system is not a black hole. So if you send in a ticket, you will hear back from somebody with help. Plus in that ticket, please give us as much, heads up as you can to help us just not write back to you and say, what are you talking about? But please send in a ticket and let us know what's going on, and we will help you solve your problem.
Thank you.
John, I had to mute you there for a second.
Gotcha. Not only can you use MPI and OpenACC together, but that's a very common mode of operation. That's why we'll talk about that more at the hybrid computing talk at the end of the week. It is, as you can see, these big machines that we've looked at so far, including bridges, they have lots of nodes and lots of GPUs. And the only way to use more than one node at a time is MPI. And the way to use the GPUs, we'll find is OpenACC. So mixing OpenACC and MPI is common. Okay, once again, for those of you that want to use the profiler, make sure you edit into gpu.job, edit in that export command, and then when it runs, because that flag matters at runtime, doesn't know about compilation, it works at runtime. So look at edit into gpu.job, so when it runs in the job, that flag is set, and then when your output comes back, it'll have the profiling output there. So it's not a compile time thing, it's a runtime thing. Okay, with that, I am going to officially start my own lunch break here, which means mostly I'm going to reboot this machine. So let's look at a solution. My solution is particular code. Here's the C1 first. We'll go over Fortran 1 after this. So here's my first pass at a solution. And the first thing I did was I said to myself, and the approach you should take is, I'd like it if this whole thing could just sit on the GPU. I don't want to move data back and forth if it can be avoided. Can that happen here? Well, yeah, this whole problem fits on the GPU. The CPU doesn't really have to do anything interesting or useful here for me. So why don't I just keep the whole thing on the GPU? And indeed, that was my approach. So I said, okay, let's put a data region here at the beginning of the while loop. The whole simulation's running. Let's move temperature and temperature last, the two things I care about, onto the GPU. And somebody asked, what about DT or any other variables that might be floating around here? I don't care about scalars. Let them copy back and forth or do whatever kernels think should happen. That's fine with me. The things I care about are the ones that take the time, which is temperature and temperature last. So I said, yeah, let's put them on the GPU at the beginning, let the whole simulation run there, and I don't need the answers until I'm done. So I did that, and things sped up all of a sudden. I said, oh, I'll stop all those copies. Except not quite, that's not quite perfect, because when I go to print stuff out once in a while, that does need to happen back on the CPU. The CPU does all the IO and the print statements. This is not inside of a kernels region. So back here, I said, well, you know what? I do want to get back temperature every once in a while. I don't want it every iteration. That was very expensive. But maybe every 100 time steps, I'll grab a copy of temperature back when it's doing the printout, and that'll still be pretty effective. And so I updated this, and now my output looked good. And indeed, this is a fine solution. And if you did this, you got a substantial speed up, and everything runs in less than a second. So if you did this, you're on the right track. Now, as a more, let's say, experienced or had more time to work with, however you want to think of it, programmer, I could go ahead and optimize this a tiny bit more and look at this and realize that, you know what, temperature doesn't really ever need to be copied in here, because temperature, as soon as this whole loop starts, gets bootstrapped based by temperature last. On our very first iteration through here, we're using temperature last, which is brought in from up above in the code. So temperature doesn't need to be copied in here at all. So there's no point in that. So I could just do a copy out on temperature. And then I looked at it even further, and I thought, you know what? Temperature last has valid results on the way out of this loop. I don't even need to copy out temperature. Final results are in temperature last. So temperature really doesn't even need to be copied in or out. Therefore, it could be a create, which is kind of the way of saying temporary variable. It's a create variable here. Just create it on the GPU and ditch it there when we're done. So I could do this as a slightly better optimization. Now, when I do that, it's not a huge improvement. And so if you didn't see this subtlety, no big deal. You didn't save a ton. All this does is save one copy in and one copy out. That's not a huge win. The huge win was saving all these many copy ins and copies out, 3,000 of them for each one of these loops that was happening before. So temperature, saving one copy in and copy out doesn't bump the difference, a 100th of a second. So it's a tiny little tweak, but it's not important. And if you missed it, no big deal. As a matter of fact, there's even one tinier more optimization that I thought was pretty low hanging fruit to pick off. And that's when I update the temperature to print it out, I'm only printing out that bottom corner. If you actually look at what we're printing out, we're not printing out all million elements. We're only printing out that bottom corner. So as a matter of fact, all I really need to update is the small bottom corner of that temperature array. And then everything is, it's not wasting even every 100 time steps, it's not wasting that extra 99% of the array copying it. So this is pretty optimal. But again, if you just did this, you got well below a second. You got 99% plus of the gains. These are just a couple of tweaks that if you didn't think of, that's fine, but I hope you understand at least. So look at my extra little optimizations here and at least go, oh, I get what's going on. You should understand them, even if you didn't have the time here to puzzle through every one of them. And they didn't have a major impact on performance either, but you should understand what's going on. Now, Fortran solutions, exactly the same thing. Like I said, you start out and realize if I just do a copy on temperature and temperature last, that things speed up a whole lot. Then I look at the output and say, it could be a little bit better. Or could be something besides zeros. So I should maybe update it every 100 time steps. And that's a pretty good solution. But then I also could tweak this a little bit. And I also, to make it, to eliminate those extra couple of copies. And then I could also update this to just do the part of temperature that we're printing out. So those are my couple of solutions. And if we do those, we find out now that, hey, we all of a sudden do have a win. Now we're well below a second in performance. And again, all three of those solutions are all about in the same ballpark here, 0.6 seconds or so. So those last couple optimizations just save a 100th of a second, basically. And now all of a sudden we're getting something out of the GPUs. So this is a big win. And let's see if we have some questions now about this. So I hope, like I said, everybody can understand, you know, at least what, you know, what this solution is. Let me scroll up and see what we got here. Shouldn't use copy in and not copy at the first line, because copy out to the host as well, which we don't need. I presume that somebody does want the full final solution later on. So yes, we could just abandon our entire simulation here, but I'm presuming that in the real world, somebody ran the simulation for a reason, and down here they would print out all the million elements. They're not just in this update's just to make sure things are going right, but I presume somebody really does want the final solution, and they do want temperature last to, you know, to carry out the final solution. So even though we don't print it out in our code, that seems like a logical, not a insensible request. We had if loop in the kernel to avoid updating the host. I'm not sure exactly what you mean by an if loop in one of these kernels. So I'm not sure what you mean there by that. Maybe elaborate on that a bit. If you didn't have the update in there, go back and look and see your prints, because otherwise, if you don't have this update in here, this is happening on the host or the CPU, right? All the actions happening back here on the GPU, and we told it it's not allowed to copy data back with our data region. So if you have the data regions but you don't have the update here, if you look at what you're printing out, it probably was zeros. It's not. Let me know, because it's magic. See, should be temperature, my indices, and I think my indices are right here on this. Would you ever update within for loops, or is it dumb? Well, if I'm doing updates in a for loop, I'm moving a lot of data by definition, right? So I mean, depending on the context, you know, it might make sense to do an update, but if it's in a for loop, it's moving data repeatedly. That's the whole idea, you know, whole notion of a for loop. So you could have one in here. I mean, this is an update inside of a loop, right? It's a while loop instead of a for loop, but there's an update in there. But you know, it makes sense in this case. So you could do that, but depends on the context. You create temperature, but the arrays don't fit in the GPU. Well, we can't do create. We did create temperature here in the GPU, and that's just fine. It doesn't save any space in the GPU, though. It creates that in the GPU. So it takes this is being created in the GPU. It's taking up that space. And if things don't fit in the GPU, which is a big problem, a lot of times, as we said, GPU memories are typically much smaller than CPU memories. And so, you know, what about things don't fit in GPU is a very common question. And the answer is then you've got to slice your problem up into pieces and move it onto and off of the GPU. We'll talk about that a little bit more in the advanced talk, but you could see you have the tools to do that now. So if our Laplace code, for example, if our plate were so big that it couldn't fit in the GPU, we could move a chunk of the plate onto the GPU and compute it with these array shape commands, and then work on, say, a quarter of the plate, then work on the next quarter of the plate. So we shuffle things onto and off the GPU. And that's not uncommon for problems that, you know, are much larger than the GPU memories, which are typically limited to, you know, dozens of gigabytes. In OpenMP versus OpenACC comparison, how many threads were used for OpenACC? Well, that's good. We haven't specified that right so far, so that's a good question. And the answer is we don't typically think of a GPU in terms of threads. We'll look at how many cores are on different GPUs, and it varies a whole lot from one generation to the next. Instead, we just want to use the whole GPU. So the quantity of GPUs you use is usually, we used a GPU, or we used 2 GPUs or 4 GPUs. We usually don't worry about the cores because we haven't had to worry about it in our programming, and we usually hide that from ourselves. Now we'll get on the advanced OpenACC, and we can look at how many cores there are, things like that, and how they're broken up into units. But in general, we just say we use the whole GPU. That's the normal way of thinking about using a GPU. We use the GPU. And you compare a GPU against, you know, a multi-core CPU. Asking how many cores used on a CPU is a much more typical question because people don't use all the cores on a CPU, and CPUs by default. Can we vary the number of GPUs being used per batch job? Yes, you can. You can specify in the batch job how many GPUs you're asking for, but this code will only use one GPU at a time by default. So there's no point in doing that yet. Look at using multiple GPUs in a bit. Can't we do printing from the GPU so we don't have to update this 300? Well, the answer is, what's a GPU attached to? Is it attached to I/O devices? More than printing, it's typically disks, you're saving results to. A GPU isn't attached to I/O devices. Now, that said, kernels these days are pretty smart. If you put I/O in a kernel, it might move some data for you and everything. So you can play around with that a little bit if you want. But at the end of the day, it's still having to move the data to the CPU. The CPU is attached to the hard drives and your screen and everything else. So GPUs just don't have output. So when we talk about the things that you need to do on the CPU, I/O of any sort, and again, in real production codes, it's mostly disk I/O you're worried about. To get to the disk, you got to go through the CPU. GPUs just aren't connected to anything other than the CPU. Are we still having high copy in, copy out for DT? Well, the answer is, if you look at it, see what's going on, the answer is yes. On the other hand, we also need it out every iteration for the while loop, so we don't have a choice. But the bottom line is, who cares, because it's only 8 bytes. So we don't really care. It won't make much of a difference. And if we manually control it ourselves, we've got to make sure it goes in and out anyway. If we stuck it in up in the data region, then it wouldn't get updated and our while loop wouldn't know what's going on. Explain the indices in the update host command. Sure, in this case right here, sure. We only, if you look at the print routine, I won't go back to that slide, but we only print out, when the code's running, right, it's only printing out 5 little elements from the bottom corner. So to update the entire temperature array was kind of wasteful. Not that expensive, didn't have a huge impact on our performance, but if I wanted to be a little bit more optimal and clever, I could say only send the bottom square, the 5 by 5 bottom corner square, because that's where all the data we're printing out is coming from. So I'm only saving the tiny little square in the bottom corner instead of sending the whole array back for the print statement to use. The Fortran and C indices are not the, so if the indices, go back to the shaping slide before anybody gets confused. Remember, there's a different standard for these two here. In C, it's beginning and length. In Fortran, it's start and end, which is the standard way these languages work. So if you're proficient in those languages, if you're a Fortran or C programmer, these are kind of more comfortable to you, but it means the indices are different. They're not the same thing. Happens to the size array larger than accessible GPU memory. You will get an out of memory error. That's not an unusual thing for somebody to get an out of memory error when they find out that, yes, indeed, GPU memories are smaller than CPU memories. And that's usually the first step on somebody realizing that, yes, they're going to have to slice their problem into pieces and move it on to and off of the GPU themselves. So out of memory errors happen. You don't have to worry that your code will be corrupt and you won't know it. You'll run out of memory, and then that'll be your introduction to taking your code to the next level and breaking it into pieces, if you have to. And maybe your whole problem is less than 40 gigabytes or whatever, and it fits. Adding the update host should not be a significant amount of time unless you're doing it all the time instead of inside the if statement. So make sure you're only doing it when you need to, every 100 time steps. So, okay, well, I'm happy to come back to this as much as we have to, but since we caught up with the questions, we'll move on. So how about we can now really compare OpenACC and OpenMP, or maybe we think we can, maybe we're not really being fair yet, because this is still a very small problem. And so this is only 1,000 by 1,000. That's trivial for modern scientific simulation problems, right? It's only 8 megabytes of memory. And as I just got done saying, modern problems are typically hundreds of gigabytes or terabytes of memory. That's the reason we have those kind of nodes on bridges. And so this is a tiny, tiny problem. As a matter of fact, on CPUs, the thing fits into cache. On GPUs, it doesn't take up hardly any space. So we're not quite fair yet. We may want to go to a larger problem to start getting a better idea of how well these play out. And indeed, for a more challenging problem that we sometimes do when we have the wide area classroom, we have 10,000 by 10,000 version of this problem. And this starts to be a little bit bigger. Now we're at least, 1.6 gigabytes. And the serial code, one of the reasons we don't use it for our test problem here is that the serial code alone takes 2,100 seconds to run. So it's no fun to do little timing tests with, but it is a more substantial problem. And there we can start to compare things, and we can start to see that OpenACC and the GPU really start to take a little bit more of a lead over the CPU. So this is a very good GPU problem, but it needs to be a little bit more realistic with size before it really pulls ahead of the CPU. But it will do that if we scale the problem up. Why are we updating the specific indices of the temperature array? Because those are the only ones that we print out. We're not printing out the whole temperature array. We're only printing out a small piece of the temperature array. So that's why we're only updating that little corner. Okay, one of the things that people sometimes get excited by, because it seems like it eliminates all of this data movement, data management stuff that we have to do, which for GPU programming is, probably the biggest pain, is that NVIDIA has something that from the marketing perspective is great, but it's very misleading, which is that they have this unified memory technology. They introduced it a good while ago at this point, and it basically says that it moves memory automatically for you whenever it's demanded. So you don't have to do any data management. Instead, whenever the GPU accesses something, it'll grab that chunk of memory from the CPU and move it back, move it to the GPU automatically, and then it'll do the reverse. So it's like paging memory. For those of you that are familiar with operating systems, it basically is like paging virtual memory. It has kind of a paging system. It will only move things when they page. And that sounds great. Only problem is it goes right back to doing the same thing that Kernels does stupidly, which is move things all the time. Instead of thinking about the big picture, can we just move things in one big chunk and leave them there? And so unified memory really doesn't do anything except let people get a problem running really quickly because they don't worry about data management, but really poorly. And so, and if you really pin somebody down at NVIDIA or anywhere that uses this and say, hey, does that unified memory work? Oh, yeah, it works great. Oh, really? Does it give good performance? Well, no, but your problem will start, we'll get you going real fast, and then we'll optimize the data movement. Oh, so we got to do the data management anyway is the answer. So you'll see this again, presented as, oh, this is a way to not have to worry about data management, but it really is not a solution for that. It's just a way to get a code running poorly, but quickly on a GPU. There's some further speedups. We're going to look into those with the advanced OpenACC stuff, but they're not going to give us any big wins. They're going to be very marginal at this point. We've gotten the big wins right here with just a few directives that we had. So in other words, are we living up to my early claims that this is high level? No, so it looks like it, right? We only have a few directives in our code. We haven't had to dive into CUDA or even talk about the innards of a GPU at all. Single source, same thing. We've got our serial code still lives on. We just got some directives. Is it efficient? Well, we'll look at a few advanced OpenACC tweaks that we could do, but I'll give you the spoiler right now is yes, we're not going to improve this code much at all, even going to a low level. This is very, very close to optimal efficiency. Is it portable? Well, find out. Move this back to your laptop, install OpenACC capable compiler on your laptop and give it a run, and it will work right there. And it was incremental. We could again go and just look at the parts of the code we cared about and ignore everything else. So I do believe that it's living up to my early claims. And again, to put this in perspective, this recurring slide right here, you can see the ground that we've covered. Yesterday we did OpenMP and we learned how to use multiple cores. And today we've covered, at least so far, the basics for you to be able to use a GPU. So pretty much any modern scientific workstation, you're well positioned to really use the hardware well, which when we started out yesterday, I said, if you don't use this kind of stuff, you're going to run at a fraction of a percent of the potential hardware speed. Now we're starting to use the hardware, near its capability. Still haven't gotten to how to do this across multiple nodes yet with MPI, but we're working our way there. And we'll find these tools will be used when we get there, that we'll use these with MPI to make things work. Okay, let me pick off any questions now before we move on to our next topic. Okay. So use copy out instead of update host. Well, copy out is going to be a region. So try what you're trying to do. I'm not sure what you're trying to do. Try what you're trying to do and see what happens. But well, it sounds like you're trying it there. But copy out is going to be a region. It's not going to be on a single line. It's got to be around some section of code where it's going to do things. So. Okay. let's see, I'm not sure what this question is. Uses a lot of VRAM. I missed that thread up above here somewhere. I'm sorry, I don't, that somebody replied to there. I'll try and catch up with that the next exercise session there. Let's see. If there are multiple accelerators, how to find which one is the device. We're going to get on that in advance in just a moment. What do we need to install on our laptop to use OpenACC? Any of the compilers I listed earlier on at the beginning slides of this talk will work just fine. So I would recommend the one we're using right now, the PGI compiler, or the NVIDIA compiler it's called now. Their community edition is free. So I'd suggest that because it's got the best performance. If you've already got a recent version of the GNU compilers, those are probably the most popular compilers by default sitting around. As long as it's a 10x, 10 point whatever version or newer, you can play with that. But I'd recommend the NVIDIA one, since it's just no surprise that it's the best for working with GPUs. Yeah, if you have any difficulty finding it, it should be pretty clear how to get to the link for the community edition of it. Let me know. I didn't put that link in the slide because it's a moving target and I don't want to keep track of it, but it should be easy to find. Okay. You mind finding accelerator again? Accelerator is a more generic term than just saying GPU, because there are some alternative devices we'll talk about in the OpenMP and GPU computing thing at the end of the day. Most notably, Intel had the Xeon Phi things that are kind of gone now. And there are, digital signal. There are other things that OpenACC is meant to work with. So they decided to use a generic term called accelerator, which by definition is any device you can plug into your motherboard to accelerate the computing. So that's the generic term. But for practical purposes and for everything we're doing here, it just means GPU. When you hear accelerator, if you say GPU, it'll be the same thing. Okay, so onward to this little topic here, very short talk. But I broke it out because I think people don't appreciate, even people that are using OpenACC, how easy it is to use the many CUDA libraries, or now increasingly OpenACC libraries that have existed over the years. Because as I mentioned, you can write everything yourself if you have to, but it's nice if somebody else has already written some, math libraries and searching libraries or whatever for you. And there are a ton of those out there. There's a tremendous ecosystem of CUDA and OpenACC libraries that you should be leveraging. And it's very easy to access those from OpenACC. And so we'll look at an example of how to do that. So I won't step through, there's a little appendix on here. I haven't updated it in a while because I don't even try to keep up. You should just, anytime you're doing something that seems like it should be a library, do a Google and see if somebody's implemented a version that you can use for your GPU. But there are tons of them out there already with all kinds of different functionalities. So we're going to take a look at one that's a pretty prototypical example, an FFT library. So an FFT is the kind of thing, yes, you could write your own. You could copy out of a numerical recipes book, but you'd be silly to do so. And it probably wouldn't be nearly as optimal as the many fancy things that are implemented in the official professionally implemented version. And so we're going to use the CUDA FFT library, but we want to use it with OpenACC. Can we do that? We're going to find out the answer is yes, very easily. There are a couple of minor things we need to learn to do that, mostly how to allocate some memory. So the OpenACC directives give us this thing called the device pointer that tells OpenACC that this is a memory pointer to something sitting on the device, right, on the GPU. So on the GPU, this stuff is already sitting there. I'm going to tell you where it is, and your OpenACC code can just go ahead and use it. You don't have to worry about how it got there. So we don't do the data management. It just is there. And that's good because the CUDA libraries will just churn away on stuff on the GPU and leave the data sitting there, leave the process data there. And your OpenACC code just needs to know where it's sitting so it can come along and pick it up and use it. So here's a very simple example right here, but we have to introduce one more, like I said, additional little level of detail for you to worry about if we're using these CUDA things, which is memory management. CUDA requires us to do a lot of manual memory management, but we don't have to worry about all the low-level stuff CUDA does. We just have to cut out some big chunks of data of memory for our data structures that we're communicating to CUDA and CUDA sending back to us. So in this case, we're going to find ourselves using the CUDA malloc command. That's a memory allocation command to malloc some data. And then that gives us a chunk of data that we can then, if we had a CUDA code right here, this is some CUDA looking kernels here. Said it's not standard C, it's this funny CUDA stuff. We could have a piece of CUDA code that does whatever it does with this chunk of memory A. And this CUDA code here is something we might have written ourselves, but it could also be a big CUDA library. And we're going to use the FFT library as our example. But anyway, the point is we allocate some memory. CUDA does its thing with that chunk of data. And then we're allowed to go and work with that with just normal, nice, high-level OpenACC, C or Fortran code ourselves. And the way we do that is we have a routine here, for example, ourselves called increment here on this code. And all we need to make sure we do is we tell our OpenACC routine that this data coming in is actually a device pointer. It's not a regular memory pointer like it would be sitting on our CPU. Instead, this is data sitting on the device, the GPU. So this is a pointer to stuff on the GPU. We can do our thing on it. In this case, we're just incrementing it, all that data. We can do our thing on it, and boom, there it is. So and then we can call a CUDA routine again if we want. So it's basically, as long as we pay a little bit of attention to where we're allocating some chunk of memory to work with, we can use CUDA and interleave it with our own OpenACC. So let's do this with and that's device pointer clause. Let's do this with, I'll skip ahead here, with this particular example, which is going to be CUDA FFT for a 1D convolution. So some of you out there probably know what this is because FFTs and convolutions are commonly used in all kinds of different areas, signal processing, and well as even differential equations and whatnot. But at any rate, if you don't know what it is, an FFT is basically just going to transform a signal from a frequency space back to a signal space. It's just a mathematical transformation that's of general use to a lot of people. And we're going to use the CUDA version of that routine here. But after the CUDA version does its thing, its library thing, we want to do some of our own custom stuff. We're not just, using the library doesn't do everything you want to do typically. Instead, you've got your own code. So we've got our own OpenACC code here, and we're going to use that to mess with the signal a little bit. As a matter of fact, in this particular example, we're going to do a multiply and scale on all the data in that signal. This, by the way, is an NVIDIA example I'm using right here, and you can follow the exercises directory has the full thing. So this is from my buddies at NVIDIA. They have a slightly different philosophy for their examples. So if you look at the source code, it's a couple hundred lines because it runs itself in serial and checks its results and does a lot of stuff. You notice my examples, I try to strip things down as tersely as possible. Theirs do all kinds of error checking and everything else. And so it's a couple hundred lines. So we're only going to look at the interesting part of the code. But if you want to look at the whole code and run it, it's sitting there in your example or your exercises directory. So point is, we're going to call an FFT CUDA routine. We're going to mess with the data ourselves using regular good old OpenACC, and then we'll call another FFT to transform the results, because it's typically what you do with FFTs. You're transferring from a time domain to a signal domain or a frequency domain and vice versa. Here's the parts of code that's interesting. And again, the whole thing's sitting there, but here's what we care about. First of all, we need to allocate some memory for the chunks of data that we're going to use. And so this is where right here, we've got the standard good old memory allocation right here for the host version of it. So the H underscore is the host version of the CPU version of our data. And down below, we'll find these things. D underscore, that's the device version of the data, or the GPU version of the data. So we've got on the host, we've got the signal, and we've got this piece that we're dragging over the signal. It makes it a convolution. So these are the two pieces that we have up here. Down here, we have the two pieces that go on the GPU, and we allocate them with CUDA malloc. So this makes memory on the CUDA device. So again, if you're not really comfortable with memory allocation and doing that kind of stuff, don't worry about it. This is all you need to worry about. You need to master is just kind of cut and paste this. Say, here's my chunk of data on my host. Here's my chunk of data on the device. And from there on out, you're good to go. So, this is the only ugliness, as it were, to interface. Down here, we have this is allocating the memory on the device for the signal. Okay, so here's the part where where the action happens. Here we've got the CUDA routine that we're calling. This happens to be called, this CUDA routine happens to be called CUDA FFT, execute complex to complex. So it's got its typical cryptic CUDA name for the routine, but it is meaningful. So this is the CUDA FFT that we're going to call. We call it on the device and on the signal and on the filter. So we're calling a couple of CUDA routines right here on the data that we already allocated. Down here is our OpenACC routine with the nice name of complex, pointwise, multiply, and scale. And we'll see on the next page the source code for this. But this is just a nice, normal, high-level C code that's OpenACC. So this is our code right here. And then once again, we're going to call the library again, because typically, like I say, FFTs are called like this. So we got a CUDA routine library that we're using. We got our own code, and we got more CUDA code. And here is our library that we're using here. And all we needed to tell our library was that, or not our library, this is our own routine that we're using here. And all we needed to tell our own routine was that these two pointers coming in here are actually from the GPU. So this is data sitting on the GPU. So then OpenACC knows that this stuff's already sitting on the GPU and it can just refer to it there. And here is our a loop down here that we're going to do to modify the data. And this just does this pointwise multiply and scale on the data. Nothing particularly profound, but it's just some nice normal C code. So there's no CUDA involved at all here. So this is how you do the interfacing with CUDA libraries. I won't belabor the point because it's just as simple as, yeah, make sure you get this CUDA-malloc thing sorted out right. And then it's very easy to use all the libraries that are out there. You do need to make sure you link correctly with things when you compile and whatnot. So there are a few details there. No big deal. This particular code, like I said, NVIDIA's examples tend to be very large and comprehensive. So when you run it, it times itself and checks itself against the serial solution, does a bunch of stuff, and you can see the results when you run it. But the important takeaway is that this is all you need to do to have CUDA code library routines that your own code uses and interfaces with. It's not complicated at all. It's very straightforward. So with that in hand, then you can go ahead and use the many, many libraries, of which I've just got some random sampling here in this appendix. But don't take this as comprehensive at all. If you've got, if you believe that a library could exist to do what you're doing, take a second and Google it. Go Google CUDA version of a rated sort and see what shows up. And these days, it's a very mature ecosystem. You're going to find an awful lot of routines out there. Okay, let's see here. What is better in terms of performance, using the CUFFT serial code with OpenACC, or use the CUFF CUDA code and interoperate with? In this case here, we've got our own code is not doing the FFT. Our code is doing something that's not the FFT. So we're using the CUDA FFT, and then we're using our own code to do something else, and we're using another CUDA FFT. So we don't have a choice, because so it's always better to use the vendor's library. It's always going to be more optimal than you're writing. So in this case, we're doing the smartest thing. We're using the vendor library, which is much better than any FFT we'd write. And then our own chunk of code is not an FFT. It's doing this other scaling of the signal. So if you know signal processing, you have a clue what's going on. But if you don't, it's just, take my word for it, it's just doing some other operation on the data. And then we're calling another FFT. So you want to use the libraries. And this isn't just true for OpenACC, it's true in general. Use libraries whenever you can. And then when you can't, you use your own code. And the nice thing here is our own code can still be some really fast, efficient OpenACC code. And using these CUDA libraries, you run into the issues you mentioned earlier about CUDA rapidly changing and cards changing. Nope, the people that support the libraries run into that issue, and they have to worry about it. So the people at NVIDIA that support these libraries, or elsewhere, there's lots of places besides NVIDIA that contribute CUDA libraries. It's their problem to deal with the support issues, and the fact that when a new card comes out, they got to go back and tweak everything silly or even do rewrites. That is their problem. You just have to download the latest version of the library. So it's nice that we hand off all of that pain to them, the CUDA pain to them. In practice, developers use libraries and modify it with OpenACC for their applications. In practice, people all use the CUDA libraries wherever they can. It's silly not to. And then we're not modifying the libraries with OpenACC. We're interfacing with the libraries with OpenACC. Modifying the libraries is not something you want to do. If you dive into, for example, this FFT library, you're going to rapidly find yourself way in over your head unless you're an FFT expert, because there's so many optimizations and tweaks and stuff involved in there. So you don't want to modify the libraries. You want to use the libraries like a black box. And by the way, I don't say that casually. I'm dismayed by the fact that people these days will grab libraries from random places on the internet, particularly with a lot of like Python or whatever software stacks. Just grab some random library that just some amateur put together, stick it in your code and pretend that that's good and robust. That's nightmarish support and performance issues. But in this case here, when you grab these libraries, are typically very, very professionally supported when they're coming from an Intel or an IBM or an NVIDIA or a compiler writer. So these libraries you don't want to dive into because they're so well written that they're very optimal. So you grab these libraries and treat them as a black box, and that's the smart move. CUDA library Fortran's process the same. It is the same, and you do have to have pointers, but that's device pointer and Fortran's fine. Fortran's actually comfortable with pointers. It just doesn't by default choose to treat everything as pointers. Do we need to use CUDA-malloc in the 1D example, or is not relevant in this example? Yeah, so this example we just had did use CUDA-malloc. So our 1DFFT, absolutely, that was the mallocs I was stepping through right here were for this code. So this is what you'll find in the source code up here. You'll find these mallocs up there. So the memory allocations to set everything up are pretty much the main pain if you're using a CUDA library. You gotta make sure you do this right. And then we could just come down here and call the libraries because the memory's already been allocated on the device and on the host. What software did you create this figure CUDA? I'm not sure which figure you're referring to, so I can't tell you. Tell me a slide number, I can tell you. Although you better be quick because I'm about to move on to the next topic here. Because like I said, I didn't want to spend a lot of time on this, but it was worth breaking out so you remember distinctly, hey, all that whole ecosystem that's been developed over the past 15 years at great expense is all available to you as an OpenACC programmer at a nice high level. You don't have to dig into the nastiness or the support issues. Okay, with that behind us, let's move on to the advanced OpenACC. And just like yesterday, I want to emphasize again that I want to just expose you to all the OpenACC capabilities. I do not want you to get intimidated and think unless you master all this stuff, you can't use OpenACC. I hope you appreciate the great results that we got with the relatively small number of directives that we've used so far. Kernels and a few data management commands, we got great results. And you should expect generally to be able to get great results on your own codes in a wide variety of different circumstances and algorithms with those tools. But now for the cases that don't fit there, or the cases where you're really upset that you're wasting 5% of the idle cycles on the cores and things like that, we'll dive into the advanced stuff. But don't let this intimidate you away or make you not realize how competent you are with just the basic tools we've already covered. Okay, so let's go ahead and look at some advanced stuff. Well, we're not just going to go through the whole specification, although you could do that. By the time we're done, we will have covered most of the specification. Instead, we're going to finally, for the first time all day, talk a little bit about GPU architecture. And this really is a remarkable thing in that, you know, again, any other approach to programming GPUs, and not just CUDA, there are a number of other approaches we'll talk about, things like OpenCL and whatnot. If we were to use any other approach to programming these devices, we would have started out talking about the architecture before we would have dared to write a single line of code. We haven't talked about the architecture at all. Things have been a complete black box, and yet we use the device efficiently. But now we might want to be, be a little more advanced. We might want to target the architecture a little bit more detailed. We might want to target a particular card and take advantage of its features, for example. And OpenACC allows us to do this without diving at a low level into things. We can do it at a higher level. And so that's what we're going to do. But first, let's take a look at the kind of specifics we might want to target, the variations that happen. So here is the Volta GPUs that we've been using today. And this is the next to latest, greatest version of GPUs. And it has thousands of cores, which are the little tiny green dots that you can barely see because they're barely a pixel in this slide right here. So we can zoom in on this a little bit. Here is one chunk of those cores called an SM, streaming multiprocessor, and here's it magnified. And so now you can actually see the individual cores inside of one of these. So now you can see how that there are indeed thousands of cores on this card. So this is a modern device, and indeed it has thousands and thousands of cores on it. Those cores are arranged in these this pattern right here, which is chunks of SMs. And the reason they're in these chunks is that the SM is the unit that actually issues instructions and coordinates things. So they're not entirely independent. Unlike a CPU cores, which are entirely independent, right? Our CPU cores can go off and work on completely different things, completely different programs, and typically they are. And with OpenMP, we can send threads off in different directions, and the cores are entirely independent. GPU cores are not independent like that. They are synchronized together. They work, they do the same instructions in lockstep with each other in chunks of basically SMs. And we'll also talk, there are smaller chunks and warps that we'll look at where they actually can branch at a lower level, but basically they're coordinated in these chunks right here. So we'll see, there's also some more hierarchy to this we'll get to, but they're not just a bunch of 4,000 independent cores sitting around able to do their own thing, like if we scaled up an Intel chip to 4,000 cores. Of course, we can't do that with Intel chips. We can only scale up to dozens of cores, but the memory hierarchy, if we peer into this too, we'll see some memory sitting here on the ends, and we see some memory scattered around in here, and here's some cache in the middle. The memory hierarchy for these things is a nightmare. And again, this just happens to be one particular model of card. If we go on to a different vendor or a different card or a different generation, this stuff all changes. But here's kind of memory hierarchy we have. We have our main memory, which is, most of the high bandwidth memory out here, which on the 16 gigabyte card, for example. And then we have caches at different levels, texture memories, and we have all kinds of different things private to different, close to different components, to the SM or to all over the GPU. So we got a lot of stuff going on here, right? The kind of thing you don't want to keep track of. And especially because, like I said, it changes from one vendor and one card to the next. Here's the typical CUDA execution model to take advantage of these things, is that we say a software thread runs on a CUDA core. Okay, sounds similar to what we did with OpenACC yesterday. We say a thread runs on a CPU core. But right away, there's one big difference here, and that is that our threads on the CPU take a lot of time to start up and get going and to shut down. And so we hope they do a lot of work. On our CPU, we said our threads might, for example, run an entire tab of a web browser. Your thread might hang around for hours or days just doing that web browser tab until it gets killed. In our codes, where we were breaking up our for loops, we hope that our threads at least have thousands or hundreds of thousands of math operations to work on at the very least. And we might even hope they hang around and work on that array time after time. So we hope that our threads have a lot of work to do, because they take at the very least hundreds of cycles and typically more to set up just to get going. So we want them to do a whole lot of work. We want them to hang around a long time. A thread on a GPU is much, much lighter weight. A thread on a GPU might only hang around to do a couple of math operations and then disappear. And that's okay, because they have virtually no setup or overhead time. And so there's no overhead. So we can launch threads that do a tiny bit of work and then disappear. And that sounds like a pure win, except that our threads are also very limited. They're synchronized in these blocks we'll get to in a second. But when I say thread on a CPU, you should think something like browser tab that hangs around. When I say thread on a GPU, you should think of something that does a dozen multiply add operations on a couple of values in an array and then disappears. So threads run on cores on a GPU. Now threads are organized into blocks. And these blocks are where what the SMs actually dispatch and are responsible for. And the blocks can't move around, they're tied to the SM. And a bunch of concurrent blocks could be running at once. And then the kernel, when you run a kernel, it launches this as a grid of thread blocks. It spreads them out in the appropriate way. And it tries to keep track of indices, in your arrays. And it spreads them out over the device. And it hopes, ideally, that almost everything is doing the same type of operations at the same time. Because as we'll see shortly, these things have to be somewhat synced together, or mostly synced together. Here's how they're synced together, or with warps. So a thread block has one or more warp. And a warp, they're typically almost always 32 threads. This happens to be a device-dependent thing, but this hasn't changed in a long time with NVIDIA stuff at least. So it's 32 threads to a warp. And the SM creates and manages all these executions at warp level. So it can't do anything at finer grain than warp. And all the threads in a warp do the exact same instruction. So this is where we see cores are pretty limited and simple-minded, is that they really XSEDE well when everything's doing the exact same instruction and they're all synchronized together. And if there's a branch in there, so if in your code you have if-then statements and things branch, the best the code can do is run all of the if branch for some of the cores, and then run all of the else branch for the other cores separately. So it has to run one first and then mask them out and then run the other second. They can't run concurrently. So conditional statements can be expensive because it takes twice as long. That's oversimplification, but it has to run both branches serially instead of at the same time. And that's because of the fact that these things are, again, so synchronized with each other. Now, one of the reasons that we do this, that it's set up with these limitations, is that when a warp does an access to global memory, it can combine all those memory accesses, no matter how they're scattered around, together and grab that memory in one chunk. And while it's waiting for that chunk to come back, it can work on other threads. And so it's very good at coalescing together things that are scattered around memory and keeping itself busy while it's waiting for those results to come back from memory. And that is where it's very easy for a regular CPU to waste a lot of time sitting around waiting for the memory to come back, while it's had to go fetch something from main memory, which, as I mentioned yesterday, with CPU, your main regular RAM is 100+ cycles away from the data, whereas the caches might only be a couple cycles away for level 1 cache. So this avoids a lot of that by having all these threads in flight at once and combining things together efficiently, but it depends on you having some pretty regular operations. And that's great because the world's got a lot of regular operations. Our Laplace code is very regular in the way it steps over the array. Matrix operations, linear algebra operations are very regular. And it turns out there are a lot of other things that don't seem so regular at first, but you can turn into regular operations and make run efficiently on GPUs. And so all those libraries out there that we can benefit from. So this is why it sounds impressive to say we got 4,000 or 6,000 cores on a GPU, but this is why also it's not like saying we have 1,000 times the computing power of a CPU. They're very limited to what they can do. Okay. So, and this varies, by the way, from one generation to the next. This is why I say CUDA maintenance is a nightmare because it changes. And beyond CUDA, CUDA only works on NVIDIA devices to begin with. CUDA is very proprietary. CUDA is not an open standard. So in case I haven't emphasized that enough. So CUDA is only NVIDIA devices. It does not operate on AMD or Intel. So they've got their own way of programming stuff. For OpenACC, that's not true, right? We're at a much higher level, but for CUDA, it's only NVIDIA devices. And as a matter of fact, the terminology for all the stuff we've been talking about changes. You know, NVIDIA, these streaming processors, AMD's equivalent, as close as it is a compute unit. Intel calls them a sub-slice on their new accelerators. And so like I said, the whole thing is a low-level hardware-dependent mess that is hard to keep up with, and the evolution is very rapid. And this is awesome. I am very pleased that GPUs are accelerating and getting better every couple of years. It's awesome because I get to leverage it as an OpenACC programmer. My codes do just run faster. It's kind of like the golden age of CPUs when I said every couple of years your code just doubled in speed without you doing anything. And that is wonderful at the OpenACC level. As a CUDA programmer, you might have a slightly different perspective. Now you've got this obligation to constantly be maintaining your code and updating it to take advantage of all these new features and change all these hardware level details. I showed you the CUDA code before and I said, you know, it's got this 32 in there. Where did that come from? And blah, blah, 31s. It's because of these numbers here, the way things are broken up into pieces, which change from one generation to the next, just here with NVIDIA alone. So I'd rather be on the side where I'm cheering the great advances and rapid strides in hardware evolution that are happening and continue to happen. I mean, the roadmap for NVIDIA is still alone. It's still aggressive. AMD and Intel are doing likewise things. And I'm happy that that's happening. I'm not like, oh my God, I got to rewrite everything continually. And this is continuing. The roadmap ahead is, you know, we're using these Voltas, but there are generations coming already that are already in fab and planned out. Like I said, it's a good thing for me, but there are people for whom it's a code maintenance nightmare. So how do we target some of this hardware directly? Do we just rely on OpenACC to always do the right thing? And the answer is that OpenACC will try to do a generically good thing and can often do a very good guess, but sometimes you might suspect that it doesn't really understand the hardware, doesn't even know in advance about the kind of hardware you have well enough, and you might want to tweak things a little bit. And OpenACC gives us a way to do this in the abstract. It has a way to do things that is very portable, but still gives us a way to control how the work is broken up and spread across the GPU. And the way it does this is with gang, workers, and vectors, this kind of abstraction that says we're going to break our work up into pieces. We have vectors of work, which we haven't talked, I keep mentioning vectors, but we haven't dived into it a whole lot. A vector is basically just a strip of data that's doing exactly the same operation across it. So even modern just CPUs have these vector instructions that just grab a chunk of data and we'll apply it, grab 16 bytes from memory and multiply them all by 2 and write them back to memory. That's kind of vector operation. So these very simple-minded strips of data are vectors, but you might combine the vectors together into a bunch of workers that do things, and the workers get combined together into gangs. And now, although the specification will never actually admit what these correspond to hardware-wise, because its job is to keep above that kind of hardware dependence, in reality, things map kind of like this, is that a vector turns into an actual thread, a worker will turn into one of those warps I talked about, the collections of threads, and a gang is one of these SMs, these streaming multiprocessors. So this is the way OpenACC allows us to talk about the hardware, but in a way that's generic. And if we move to a different device, like an Intel Phi accelerator, the vectors turn into vector instructions, and a worker is a core, and a gang is a whole CPU. So this is a nice way to, like I say, abstractly be able to influence the way our work is broken up. But if we do want to target a particular card, we have to dive down into the details. So here for a Kepler generation, for example, there are these heuristics, ways that it's helpful to break work up, and it'll probably work better with the card kind of thing, which CUDA people have to fight with. So it's 32 thread wide blocks are good. And then, so it tells you how to break your work up into pieces. The total number of blocks, threads in a blocks between 256 and 512 probably maps well to hardware. So these are the kind of things that you start worrying about if you want to target a particular card and wring maximum performance out of it. The nice thing is in OpenACC, we can just start adding on these clauses, these optional clauses onto our kernels or onto our loops, which we'll look at in a little bit. We can just add on these optional clauses and say, this is how I suggest you break the work up. and it'll work better probably with this particular card. So it's a way to just give some suggestions or some commands actually to tell OpenACC how to break the work up into pieces and map it to the hardware. And so that's exactly what we can do. We can play around with this. Now, here, for example, is our SAXP loop that we had before with kernels. And here is where I messed around with it a little bit and changed some of the parameters to try to get work better on a card at the time. And this is an older card, an older compiler. And by experimenting around and using a little bit of good guesstimates and whatnot, I could actually speed this thing up by 20%. I haven't touched this slide in like 3 years because I don't think I can beat the compiler anymore, to be honest with you. Compiler's getting smarter and hardware's gotten better at generic loops like this. And so this fight is, and this optimization is less worth having every day. But this is a slide at one point where I could finally beat the compiler's defaults pretty decently. And this is what it was. But like I said, if you do this on the latest compiler or on these Voltas, probably not so good. But at any rate, it gives you the option. If you decide that you don't think the compiler is smart enough, you can start to break things down. So that's the way we can do low-level hardware targeting with these kind of things here. And it's very easy to experiment with these too, by the way. If you get some guides and somebody says, oh, you look at the specs on this, this actually is, got this kind of cache size or whatever, you can go and just screw around with these, do some timing runs and see if you can do better than kernel's first guess. So it's painless to experiment. And by the way, experimenting is how this is done. Even if you're a CUDA person and you're way down in the weeds, you still don't typically find the optimal values by getting out your pencil and paper and saying this is exactly the right value. There's a lot of experimentation. This makes that experimentation pretty painless. Okay, let me see. Any questions here? Is there ever going to be a central GPU compute standard? Well, not anytime soon. When we get into the GPU and OpenMP computing thing, I'll show you how the vendors are kind of have a lot of tension between them and pulling things in different directions. So while one might hope that there would be some convergence, it's not imminent right now. As a matter of fact, the trend is very competitively the opposite at the moment. The code that's going to be executed on a GPU should want to generally avoid conditionals. And the answer is, well, recognize that your conditionals are going to do what I said. They're going to have to execute one part of the conditional and then not concurrently, separately, serially, the other part of the conditional, and realize that's an expense, right? It's not the kind of thing with the multi-threaded CPU code. You can have one thing taking the if-then branch, one core taking the else branch, and everything's fine. And they're both running concurrently, and it's no slowdown. We don't have that on GPUs. So you can do conditionals, but they're going to add some expense. They're not going to be able to run concurrently. So that is the thing to be aware of. Okay, now we're going to take a little bit of a dive to a deeper level of controlling our loops themselves. So far, we've had great success with kernels, but we can, if we decide that kernels is, isn't spreading the work out perfectly, or we have some idle cores sitting around at the end of the loop, we can take over responsibility for that. This is going to be exactly the same as yesterday with OpenMP, where we said using a parallel for, parallel do loop does a whole lot of heavy lifting, just takes the responsibility for that for loop off our hands. Or we said we had these parallel regions where we got to start worrying about synchronizing and barriers and whatnot. You can do it, but it's a lot more responsibility. So you have to decide whether it's worth it. But let's take a little journey down that path here. So we have parallel regions, and we have a parallel region, just like in OpenMP. It means all of the workers want to start working in that parallel region. They're not coordinated anyway. They're all going to charge ahead. And they're all going to try to do work all the time. And that could be good if we want to not waste any cycles, but it means we got to do a lot more direction and corralling now. So that's what we're going to do. So here's a parallel region. In the parallel region, we can specify how many gangs or workers or whatever we want to divide the region up into. And we can start to take responsibility now for which variables are private or not in that region, and reduction operations. Like, so far, kernel's worried about this for us, right? Now we have to start worrying about this stuff, just like we did with OpenMP. And so there are a lot of clauses on the parallel regions to allow us to control things. And you don't have to include them all. You can let the parallel region be a default thing as well. But if you want to start tweaking it for how many gangs and workers and whatnot are going on, you can do that. Some of the things you have to worry about, for example, you might have variables that you have to make private in that region, just like with OpenMP. So here's a parallel region. Let's take a look at how this works here. So here's a parallel region that we launched, and we decided we think this might be the right number of gangs and vector length to divide things up into. And here's our loop in that region. And within that region now, we're going to take it loop by loop control. So we're now using the loop directive and telling it to use the gangs and vectors we specified up above. So here's our manually taking control of a particular loop instead of just throwing kernels in front of it. Now let's take a look at the difference between the two. So here is kernels in front of this loop, and this is exactly the same as us making a parallel region and inside of it doing an ACC loop. Okay, that's good. Why would we do that then? What, they're the same thing? Well, the answer we're going to start to see is when we put loops next to each other, some of the cores that get done here, or the workers that get done here, can move on and do more work later on. They can't do that with kernels. They also synchronize to the end. So we're going to see how setting these things free causes us a little bit of more requirement to conduct things. But at any rate, don't do this. Do not just say parallel region and have a for loop in it, because this, just like with OpenMP, means that all of the cores are going to execute this loop together, not coordinated. They're not going to break the loop up. They're going to, each one of them is going to do the whole loop itself, which you never want to do. That's not the right thing. So you need to make sure if you have a loop in a parallel region, in the parallel region, you have a loop directive, not just a parallel region and have some loops inside of it. Big difference. Okay, so let's see where the difference might show up now. So if we have a couple of loops back to back and we put them in a kernels region, this is going to do exactly what we think. It's going to run the first loop's calculation on the GPU. It's going to finish up, and then it's going to run the second loop's calculation on the GPU. And we're going to get our answers, and it's going to be exactly what we expect, the same as a serial code. But maybe you run the profiler on this and you go, you know what, some of the cores got done here early and they were wasted time. And I think that it would be nice if they could get on to working on the second loop whenever they're done. So I'm going to take charge of this. I don't think kernels is good enough for me. I'm going to take charge. And so you do this, and you say, I'm going to put these in a parallel region and make them a couple of OpenACC loops. And this way, when they're done here, there's no barriers, there's no coordination. They're going to go work on this right away. And you go, this is great. I got the profiler on this. No wasted cycles. Wonderful. Only problem is we got a little issue here. We got a little bug we've introduced into our code. And that is that some of the cores up here are working on calculating A using B and C up here. And some of the cores race down here and start on this loop right here using calculating D using A. It is possible that some of these values of A down here are still being computed and changed up here. So some of the cores are racing down here before these correct values of A have been set up here. So cores can race ahead prematurely. They will, because we haven't done anything to stop it, and start calculating some incorrect values. So we indeed set all of the workers free, but what we did was introduce a bug into our code. So this is where you have to start being cognizant of what's going on. Maybe we need to put a barrier in here to stop things, in which case we're back to our original kernel, or maybe we need to do some other things. We'll look at some options. But this is just like with OpenMP. When you get into a parallel region, you're taking responsibility, more responsibility. So here's one way that we can begin to corral. This is a rather nice feature of OpenACC, is that we can begin to specify which loops can jump ahead or leapfrog ahead of others by putting them in different queues. So we have in OpenACC a bunch of numbered queues available to us. I believe it's 16 at the moment in the specification. We have a bunch of queues, and if we say that this first loop is in Q1, then nothing else that's in Q1 will execute until this loop finishes. Now, the second loop down here, if we look at it, it's fine. It doesn't use any of the variables that are being affected in the first loop, so it's fine. We can put it in a different queue, and it'll be fine. And then once in a while, if we want to make sure all the queues are cleared, we can put a wait command in, and it'll wait for all the queues to clear. So this is one way of saying, okay, these two loops, the cores that are done here can race ahead because this is in a different queue. Now, what about cases where they can't? Let's look here. So here we've got this first loop is in Q1. Any cores that finish up here can race ahead and start working on Q2, and that's fine because there's no variables crossed between these two. But down here, we can see we're using values for C, which could be set up here in this queue. We're using some values of B, which are set in this queue. So that means we want to make sure that this loop doesn't start ahead of these two. So we put this loop, we can put it in Q1, nothing can jump ahead in the queue, and we can also tell it to wait on Q2 to finish up. And so this is one way of blocking now, making sure that the cores can race ahead. Some of the cores that finish up earlier can get to work on here, but none of them can race ahead to here. So it's a nice way to specify our dependencies. So we can set all the cores free, but still not have to worry about them racing ahead inappropriately. This is a nice, elegant way to do that. So here's some more dependencies and just a different variation of this we could do. Again, we put this loop in Q1. Down here, we have this is in Q2, but it's going to wait on Q1. This is Q3. It doesn't care about Q2, but it'll wait for 1 to finish. And if you look, that's appropriate based on which variables need to be finished, computation-wise in which order. So this is a nice way to get at, again, not just using kernels. We can set all these cores free, let things be dangerously loose and aggressive, but then we can go back and make sure that they're correct. They're eager, and anxious, but nothing can charge ahead more than it should. And this is not that difficult to do. When we do these kind of things, we do need to be aware of the fact that we now have the private variable issue again, where we're having a bunch of cores operate on a single scalar variable. As we said, whenever we got a parallel loop in OpenMP, one of the things you need to be aware of in that loop is, do we have a scalar variable in that loop, right? A non-array variable in that loop that's being written to. And just like with OpenMP, it means all these cores are trying to set this value of X and then use it later. So we got a problem here. So we need to make X private. And as a matter of fact, if we want to use a variable afterwards as a scalar, like sum, we not only need to make it private, we need to make it a reduction. And so we can manage that because we know OpenMP, so it's no big deal, but we've now descended to that level there instead of just using kernels. If we use kernels here, it'll do all the right stuff. But with OpenMP, we've got to, with the parallel region where we're taking charge of stuff, we've got to manage it ourselves. But we can maybe be smarter than kernels, which will always, kernels will give you a correct answer, but always be very paranoid about things. So let me see if we have some questions here. Let's see. Is there an analogous instruction for schedule in OpenACC? I assume you mean OpenMP there. So is it for scheduling here? And the answer is the two differences between OpenACC, one difference between OpenACC and OpenMP, I should say, is that OpenACC has these queues for scheduling, and OpenMP, instead, we had things like tasks. If you remember yesterday, we covered tasks, and I said there's dependencies. And I said this is a really powerful feature. For tasks, we can say a dependency. So we had the ability with tasks to say, one thing depends, has an input or output dependency on particular variables. So OpenMP's approach to this problem is to have dependencies. And it can do that because it has a lot of flexibility and freedom. Each core is very, very flexible and can jump around. This mechanism, on the other hand, queues, is more suited to GPUs where the cores are not entirely independent. And so that's one of the differences between OpenMP and OpenACC is their mechanisms for enforcing these kind of dependencies is different. This one's more suited for GPUs where things are synchronized with each other, and tasks in OpenMP are more suited to where every core is entirely independent. Okay. Summary SQL has to work to do the same thing together, whereas the kernel has to work to do that. So parallel says it's not at the warp level, it's actually at the SM or worker level. So parallel says everything is just trying to execute the exact same instructions all at the same time, charge ahead. Think of a parallel region. By the way, this is kind of true in OpenMP as well. Parallel region says everybody charge ahead until some other more directives inside of this region force you to coordinate. And so that's what a parallel region is, as opposed to kernels, which says I'm in charge and I'm going to synchronize and do everything very conservatively and take charge of it. Just like in OpenMP, we had a parallel for loop, stick it on a for loop, and be sure it's going to do the right thing, but it's also going to be conservative and put barriers at the end and everything else. And we said we could go into a parallel region and just, hey, all the threads charge ahead, and we need to coordinate them along the way. So those are the two big differences in approaches. Okay, so we had our private variables. We have some loop clauses on our loops within these parallel regions. We can control things in a finer way. We have private and reduction. We know how those work now. We have these gang worker vector things to say we can just kind of take charge or make strong suggestions of how work gets spread out at the hardware level. We can also say a loop is independent if the compiler, we said kernels, will not do things if things are wrong. It might say there's dependency in a loop. You can override that if you want. You can say, you're wrong, do these independently. We can do the opposite, as a matter of fact. We can say, okay, there's a reason this loop needs to be executed sequentially. And so a particular loop inside of a parallel region, you can make it work sequentially. This is obviously going to really slow things down. You wouldn't want this to be a big loop, but you can do it where necessary. We can, once again, we talked about this yesterday, collapse loops together. If you've got loops where maybe you have something nested 2 or 3 deep, and the outer loop is goes 1 to 3, and the next loop goes 1 to 10, and the inside loop goes 1 to 100. Maybe you collapse them all together, and now you've got a loop that's from 1 to, I don't know what I just said, 900 or 9,000 or whatever. That will execute all those loops collapsed together. So that's a nice way to do it. This is really nifty. This is something that is kind of a newer, more advanced feature, which is tile, which takes advantage of the fact that a lot of times when you're doing operations on grids, and a good example of this is a matrix multiply. If you're doing a matrix multiply, the simple way you learned it, if you for those of you that recall your linear algebra, if we're multiplying two matrices together, we could take for the new element, we're multiplying a whole row of one matrix with a column of another matrix to come up with a new element. Well, that going from one matrix, grabbing a row and a column from another matrix, that's a lot of memory fetching, especially because things are going to be spread out all over memory. They do that for every element. You're all over the place in memory all the time, and you're fetching a ton of memory, and that's very expensive. And so if you write kind of the freshman level matrix multiply routine and run it on just your laptop, just a standard Python code, you just write a matrix multiply in Python on your laptop, it's going to take a long time, versus if you get more clever and say, I'm going to work on little squares of these arrays at a time when I've got the data loaded in. Then you're going to find, again, that same Python code running on your laptop can run maybe 20 times faster because it's doing a lot less memory thrashing. And so that is true at the compiler level as well, is that you can, or I should say at the kind of compiled level as well, you can take and work on tiles of data in a grid type operation and get much better performance because, again, it's doing a lot less memory thrashing. And this is something that previously was always up to a user to implement. And if you look at any real serious matrix linear algebra library, you'll see lots of this code in there to do this. It's neat that OpenACC has a tile command now, which will take for nested loops, break them into subloops into small pieces to give you some of that locality, that tiling. So this is kind of nifty. And again, for any of you that are doing linear algebra operations or writing those kind of things, this should attract your attention. Okay, we're going to find out multiple devices. We've got a lot of questions about multiple devices. We'll have some examples of that coming up. We can also control which device we're working with. So to summarize, though, this section of it, should we use kernels or should we use parallel regions and take control? This is very similar to what we were talking about yesterday with OpenMP, which is that, it's nice and less error prone to stay at a higher level and just use kernels. But sometimes you decide that you want to dive to a lower level. Sometimes in OpenMP, it's necessary because everything is in a for loop. So in OpenMP, if you want to start doing graph and recursion operations, you have to do something besides just use the parallel for loop. In OpenACC, it's usually more of a optimization call that you think you can do better than kernels can do with your own lower level control. And so, you can go either way, and history kind of says that compilers get smarter and smarter, which means you might want to lean on kernels more and more as OpenACC becomes mature. And at this point in time, it's pretty good. But maybe you can do better, in which case you shouldn't be too intimidated against using the parallel region. Okay, enough on that. Let's talk about a little bit more data management, because although we already got some really nice heavy hitters like copy in and copy out and update, there are a couple more I didn't mention. And you should never find yourself, if you're writing a GPU code with OpenACC, you should never find yourself saying, I don't know what directive will get the data there. If we only had copy regions, for example, and we didn't have update on our last problem, it would be a pain because we just want to get a little bit of data over to the CPU once in a while to print it out, right? And so it's nice that we have update. Well, there are a couple more times when you might find these nice to use. Enter data, for example, allows us to put a whole lot of data on the GPU to be used later. It doesn't need to go. So a lot of codes, for example, will have an initialization section where we set things up. We do in our Laplace code, right? We have an initialization part where we set the plate equal to 0 and we set some boundary conditions. It might be nice to move all the data over there in the initialization part of the code. It kind of makes sense, and leave it there and get it back at the final part of the code when we're outputting data. So we can't put braces around a bunch of different subroutines in our code with copy regions. So instead we could just say, enter data, load all the data on the GPU now, and let it sit there until somewhere else, way different part of the code in a different subroutine, we have an exit data region and we bring it back. And in between, we could do some updates if we want, but everything doesn't have to be one of these regions that we use with copy in. So we have enter regions and exit regions and updates, which we've used already. And by the way, we can attach to these, and we'll find this to be really useful for optimization. We can put these in queues as well, because I mentioned to you earlier that one of the popular optimizations, one of the very common optimizations you can do in parallel computing in general, is to try to overlap computation and communication. Whenever you know that communication, in our case, copying data onto or off the device takes a lot of time, you might say, well, while we're twiddling our thumbs, instead we could do some computation. So while we're moving a chunk of data onto the GPU, maybe we could be computing some other chunk of data. For our Laplace code, for example, if we had a huge Laplace plate and it couldn't fit into memory, while we're computing on 1/4 of the plate, we could be sending another part of the plate over And then by the time we're done computing, that's already there. And then we send the results back while we're computing that part of the plate. So overlapping computation and communication is really nice. Updates can do this. We can start an update or start an enter data region while, before we start the computation, before it's ready for computation. And if we want to coordinate these things, we can even put them in queues. And so it's nice. We can say, start sending the data, and down below where we've got a loop, we can say, but don't start this loop until the data is complete. So we put the update in a queue, and then down below where we have a loop to process that data, it'll say, okay, I'm ready to go, but I'm not going to jump ahead of the data getting here. Hopefully the data is there by the time you get to that loop, but if it's not, it'll wait for it. And so we can organize things in queues in nice chunks. Another thing we haven't emphasized in our examples, because I don't want to clutter up our examples or make them complicated, is the fact that dynamic memory, allocating your own memory and having variable data structures is much more common than having static data structures. For example, for our Laplace code, our plate is 1,000 by 1,000, right? It's kind of written in stone in the way our code is, the variables are defined. In the real world, you like codes to be flexible. They might read in from an input file the size of the plate and then allocate memory. And so, the real world's got an awful lot of dynamic memory. And in case you wonder, well, John's not covering a lot of dynamic memory examples. I wonder if OpenACC or OpenMP don't work well with dynamic memory. That's not the case at all. Dynamic memory is so central to scientific computing that all of these tools we're using are very comfortable working with it. So if you're using mallocs all over your code, OpenACC is perfectly happy in dealing with things that have been dynamically allocated. And so same with Fortran. Fortran has allocate for dynamic data structures. OpenACC interfaces very well with that. So by the way, there's OpenMP we talked about yesterday, and so will MPI. I just don't do a lot of that in our code because it makes it more complicated. It's nice for the Laplace code if things are statically allocated for you, especially for those of you that aren't comfortable with that notion. But when you do get into real production code, you want them to be more flexible, and typically you don't hardwire in or hard code in the data structure sizes. They're read in and defined as the code sets itself up and starts running. And that's perfectly fine with OpenACC and OpenMP and MPI. They work well with that. Let's see, you can move the data wherever you want. It doesn't need to be right before you use it. So we could, for example, move data earlier and then set up a pointer to it. And then later on, when the thing runs, the pointers are ready to go. So again, when you find yourself structuring your code, if you say, hey, I'd like to put the data on the GPU right here, because it makes sense when I'm setting up my data in my code, and not just do it all right before I compute or whatever, you can do that. It's easy enough to do with these extra directives. I'm sure a number of you are also wondering, hey, we're not using a lot of complex structures here, like C++ classes or Fortran classes, derived data types basically, and stuff like that. Does this stuff work with it? Well, yeah, once again, these tools are very serious. They're used for serious codes. So yes, they're designed to work well with very complex data structures and whatnot. Now, again, you have to be aware of certain things like, hey, can they magically solve, layout issues and whatnot with, standard template library, containers and whatnot? And the answer is no. It's a standard C++ questions you have to deal with all the time for performance reasons. The library, both OpenMP and OpenACC and MPI, recognize that real codes have lots and lots of complex data structures and complex objects and all kinds of pointers floating around, and objects that have pointers inside the data structures. So you have to worry about deep copies, but the standards are all set up to deal with that. Okay, let me see. Some questions. Let's see. What's the difference between enter data and copy? So enter data is just a one-liner that happens, says move the data onto the GPU. You can think of it as kind of like an update at that point in time, but it's assuming that the data isn't moved onto the GPU at all. It doesn't exist anywhere yet. So enter data is just a standalone move the data onto the GPU. Copy applies to a region of code and has an end to it and says move the data back off at the end of the copy region. So copy is for a region of code. Move it in here and move it off there. And also then gets stuck in has to be in a subroutine, right? Copy can't start in a subroutine and end in a different subroutine. Enter data just says, hey, move the data on here, and it can be in a subroutine anywhere in your code. And somewhere later on, you could do an update or an exit data somewhere very far away else in the code. So it's just a one-timer deal. Whereas copy is a region of code. Move it in here, move it out there. So those are the two different approaches. And they can both, one of them makes perfect sense in your code the way it's structured in one place, and another place, no, you don't want to do it that way. So there are two options for you to choose from, whichever one best fits your code. So OpenACC has a number of kind of things hanging off the end of it too. I wanted to mention, like, for example, if you're an experienced CUDA programmer, you might know that CUDA's got this texture memory, which is kind of a small cache of memory that's useful. In OpenACC, you can suggest that OpenACC take advantage of that. If you've got a small data structure that's used by all the other cores are participating in a loop, you can suggest that it put this data structure in cache. That'll give you slightly better performance. Again, this is the kind of things that allow you to target the hardware a little bit without really making your code weirdly, non-portable or tied to the hardware. So it's one of those things. The CUDA unified memory I already talked about. I said this is this supposedly magic thing that allows you to say, oh, here's an array and it needs part of this array. And so it'll grab the array and move it over slice by slice like this. And again, it sounds great. It sounds like, oh, I don't need to worry about memory management. But the reality is this will get your code running quickly, but it'll be terrible, just like our example was earlier. It'll be terrible in performance, and you got to go back and add in the memory management anyway. The spec has evolved rapidly over the past 6 or 7 years. It's really moved forward. It's kind of slowing down now. I think they've got an awful lot of what needed to be there in there. So over the years, if you look at older specifications or whatever, there used to be a lot of limitations that aren't there anymore. So I won't belabor that, but I will point out, never be afraid to go look at the full spec. As a matter of fact, the newer one, which is 3 point whatever, not this one right here, go look at the full spec. But try to look at the latest spec, because this has changed so much that if you look at a 5-year-old version of the specification, there were a lot of limitations which have been removed. Examples of that are that, now routines can call, GPU-based routines can call other GPU-based routines. So you can have, workers launch more workers. The only thing is that OpenACC needs to know kind of the hierarchy, the order of these. So if you designate a routine as a worker, it can be launched from something that's also running on the GPU, because it knows that this gang can launch these workers. And here's a worker code. So you can have threads launch threads, you can have nested parallelism, all the stuff that used to be limitations. It's gone, right? It's gone now, but it is necessary. And a compiler will tell you that if you have something running on the GPU, trying to launch another bunch of something on the GPU, it at least needs to know that it's a worker. It needs to know it's an OpenACC routine. So you do have this hierarchy to worry about a little bit. Here's an example right here. This entire thing is running on a GPU. It's kind of the dream. I said you want everything to run on the GPU, right? Well, here, this whole thing's running on the GPU, and on the GPU itself is calling this solver routine right here, which is a routine running on the GPU. Then it's calling this another version of it. So it's launching more kernels on the GPU from within the GPU. And that is just fine, but it needs to know that these are actually OpenACC routines, so it can launch these subroutines from within the GPU. So no big limitations. We've talked about the device-specific tuning here, the things we can do with different numbers of gangs and workers and vectors lengths. And you might think, okay, that's great. That means I'm going to do what you see in a lot of codes, which is have these if-def statements. So any of you that have experienced codes that serious codes, you'll notice that there's a tendency when somebody has to make a code adaptable both to one environment and another, they'll have an if-def in there, or even the debugging mode. If I'm debugging, then include this stuff. If I'm not debugging, do this. And so that's the traditional way of dealing with different devices, would be to have a bunch of if-def statements in your code. If NVIDIA, then this number of gangs. Else, Intel, then this number of gangs. And that stuff is kind of traditional, but it also gets to be quite ugly. And so OpenACC has bundled into it now the capability to say, here's a way to say, if I'm on a particular type of device, use these parameters. If I'm on a different device, use these parameters instead. And so this is pretty nice way to avoid the if-def nonsense that usually is in codes that are meant to be flexible and adaptable. Okay, there's that line continuation syntax, but we've seen that already. Okay, multiple devices. As I've said, and as many of you have asked, multiple GPUs these days are really common on bridges. All of our GPU nodes have multiple GPUs. And so it is up to you to use multiple GPUs independently or manually in your code by saying, I'm going to move my data onto or off of different devices in my code in different slices. So if I've got a giant array that's too big to fit on one GPU, or Laplace code, let's say we scaled it up so it was many gigabytes, I could put half of the array on one GPU, and then I could set the device number and put the other half of the array using these slices on the other GPU. And so I've got each half running on a GPU, and so I'm using both GPUs at once. And that means I do need to do this slicing myself to keep track of it. and I do need to make sure I've got the right device number for each half. So it's a little bit of bookkeeping on your part. I do wish that this stuff evolved to the point where multiple GPUs became like a virtual GPU combined together, and OpenACC would worry about that. That's the dream. It hasn't happened yet. So at the moment, everybody that's using multiple GPUs, which is everybody, has some kind of bookkeeping like this. If it's their problem, is going to use multiple GPUs. And there are plenty of examples of of this, but they're nothing more than just bookkeeping like this. So that's how we use multiple GPUs. We just access them by device number and split our work on the different pieces. I mentioned profilers. We're going to hold off by and large till Friday to talk about all the tools, but I can't help but briefly mention here the profiler, the NVIDIA profiler here, and how we can see what's happening with our Laplace code as we run it. So here is the NVIDIA Visual Profiler. If we throw it at our code, so it's a little bit nicer than the built-in compiler profiler. You can see it gives us some nice bar graphs and everything. So here is our first pass at this, and this is where, if we look at compute time, this is the compute time. So if you squint at the slide enough, and I don't expect you to, this is the compute time here. And there's a tiny bit of compute going on. And up here, if we look at the device transfer time, there's a ton of that going on. No surprise. We already saw that, with our little mini profiler. So this is our problem with our Laplace code. And here it is after we fix it. After we did our data management instructions, now we can see, hey, the compute regions are really, really busy. And once in a while, there's a little pause where we update the host with the temperature array every 100 time steps. So we get 100 of these really, really busy, efficient regions. Once in a while, we take a little break to update our memory to the host. And this, by the way, is with that full update. If we did a little tiny slice, this would disappear, but I thought this was easier to see. So once in a while, we update the memory. The rest of the time, we're running away quite happily. So here's our pretty much faster code. So the profilers make it easy to see these things, easier than just peering at the individual timings. Here is a code, for example, that NVIDIA has. Again, their examples are pretty large and complex, but they're also pretty nice in terms of demonstrating some principles. Here's a Mandelbrot set generation code. And if the generating the Mandelbrot set, so it's these fractal pictures you probably have all seen in the past, is something that you've done a patch at a time. And so it would be nice if the GPU, when working on one patch, could be transferring back what it did while it's getting ready to work on the next patch. And we can do that here. So we start out the code here, and we can see that this code has a lot of data transfer time. These are the PCI transfers here versus the computation time. And so we can apply some fixes we'll talk about in a second to the code, and we can overlap the computation and communication. So while it's doing, so we sliced up our communication into a bunch of little pieces. While it's working on one patch, computing one patch, it can be transferring the completed patch back. And so by overlapping all of these computations and communications, we can speed the code up a lot. And here for that particular example, which I gave you the link if you want to dig into this particular example, we can see they started out, here's a 16-core serial code, well, not serial code, an OpenMP code. It runs in 16 cores. Here it is parallelized with a GPU. Here it is where they broke it into little blocks to transfer stuff and did the update. And here where they made them a little bit more asynchronous using the queuing structure. And you can see that by overlapping the computation and communication, they got another big gain on top of just going the original GPU version. And so that's a quick step through the kind of profiler feedback you can get and how the queues can be useful to allow you to overlap that computation and communication. Here are some things we didn't cover in the talk. Let's see. I did mention briefly at least classes and dynamic memory and everything, so I guess we did cover this. There are a lot of environment variables floating around as well. Just like with OpenMP, there are a bunch of environment variables to affect the behavior. With OpenACC, if you look in the specifications, you'll see there are a lot of environment variables to set up how devices are numbered and some of the defaults for the way things behave. And they can be useful little tweaks. I just didn't want to go through the whole list, but you may want to. We talked about some of the clauses for conditional compilation, saying if there's a certain device type, do a certain type of thing. There are, much like with OpenMP, we found that there are API or library versions, functional calls that you can make instead of directives. If you don't like directives and you're willing to commit your code to being just 100% GPU type code, OpenACC code, instead of using a directive approach, there are APIs, in other words, function calls for all of that. Just like with OpenMP yesterday, we saw there's a library. Hybrid programming, we'll talk about this later, but OpenACC works great with MPI and with OpenMP, and we'll see some examples of that once you learn some MPI, but it is designed to work very well with that. Should you learn CUDA is a question that usually might even be sitting in, I haven't caught the question for the last 5 minutes, might be sitting there. And the answer used to be a little more debatable to me. Nowadays, I would say not unless you're inheriting a huge CUDA code base, because it'd be silly these days to start writing a code with CUDA. It's been a long time since I started writing a code with CUDA. So you'll still come across it. If you want to be a super, wizard with GPUs, yeah, you're going to come across CUDA code. So it might be useful to learn, but you'd be silly these days to start writing code from scratch with CUDA. So unless you've got legacy concerns, I would say no. Okay, let me see what questions I have. Let's see. Doing data copy. That's the last one question. Do we have any finance examples that need HPC? There are tons of, so high performance programming in finance is a huge active area. I target for these workshops generally more scientific examples. The big data workshop's an exception. In the big data world, a lot of my examples are very much commerce oriented, and I get feedback. Can you have more scientific examples there? But in these, these HPC programming workshops, it's mostly scientific examples. But there's a huge, very active area in the finance world with HPC. And for any of you that are familiar with finance, might know that high performance computing, and particularly low latency data processing, is worth many millions of dollars to Wall Street, to the point where they have their own dedicated microwave links just to minimize latencies and getting data and everything else. So I don't go into that, but it's a very active area, and you should have no problem finding some interesting examples there. Let me know if you can't, and I'll point you a lot of them. Let's see, I think large data. Well, that's kind of what I said. So yeah, come to our big data workshop, and like I said, we have a lot more examples of commerce and enterprise-driven stuff. Possibly use profile like terminal commands. There are, well, the profilers these days, people are really, they've switched very heavily to being GUI based, being graphics based. So the closest you can get to, so that there are profilers will output command line stuff and give you lots of text output. But I will say that that's not their priority these days, is not supporting that. Same is true of debuggers. They've all switched to kind of graphical things. Now, the good news is that they're fairly agnostic with their graphic support. So they're not just X Windows applications. They'll also give you clients you can run on Windows or Mac kind of devices. But the using the command line interfaces to debuggers and profilers anymore is a little bit painful. And I do miss that in some respects, but that's just the shift. The demand has shifted to GUI-based stuff. So they're there, but they're not, they don't do a great job of making those interfaces as clean as they could be. Is there SIMD-like support with OpenACC for CPUs and OpenMP? Well, everything in GPU world better be SIMD. The whole GPU is built around the SIMD concept. So SIMD, being single instruction, multiple data, is a term that goes back to widely used in the 80s and 90s when a lot of the stuff was taking form. It means one instruction that does the same thing with a bunch of data. And in case if you've been paying, that's what GPUs almost insist on having, is they all work on do the same operation on data at once. That's what GPUs excel at. So pretty much everything on a GPU is SIMD or doesn't work so well. And that is a little bit different from OpenMP. OpenMP expects that the cores are completely independent. So having things be SIMD there is an optional thing. That's why in OpenMP, we had some SIMD instructions to help improve the vector instructions. In OpenACC, we don't have anything like that because it just assumes everything already better be pretty SIMD amenable, or it's not going to work well on a GPU. So that's why we don't have any special SIMD instructions. Like we have vector lengths that we can tell the GPU what to do and whatnot, and that's as close as we get to worrying about it, because otherwise, if it's not very SIMD-like in nature, it's not going to work well on a GPU. Okay. Okay. Well, with that, we can move on to our. How are we doing on time? We're doing great on time. We're going to finish up early today because that was what I expected. So let's move on to our very last talk, which is going to answer a lot of the questions I deferred earlier about how things work on other devices and whatnot. And that is OpenMP and GPUs. And yesterday we didn't talk about using GPUs with OpenMP at all, because that is not OpenMP's background and history and strength. OpenMP came out of the desire to make multi-core CPUs work well and replace the fact that P threads are, so tedious and low level. And so that's what it was designed for. And that was its emphasis all the way through the 3.1 versions. However, then GPUs came along and had separate memories. OpenMP, by default, everything we talked about yesterday, we didn't have any notion of separate memories, right? Things are all shared in memory. You can make things private and make multiple copies of them, whatever, but they're all sitting there in memory. There's no idea that we need to move things. Whereas with OpenACC, we could see these data management commands are critical to getting good performance. So we needed some extension to make data movement like this something we could control. And so when GPUs came along, people said, okay, we need to expand things. Now, there are also some other differences besides the memory management. GPUs have thousands of these cores, but they're pretty simple-minded. They need to be very SIMD-like, to borrow a term we were just talking about. The threads are very, very lightweight. You can launch a thread on a GPU to do a couple of math operations. That would be incredibly expensive to do on a CPU. So we have a little bit of a difference here, but we have a lot of commonality. So when this happened, when GPUs came along, people said, we love this directive-based approach. So let's go ahead and extend it to GPUs, but it's brand new idea. And so we can't go and mess around with this established standard, experimentally. We need to spin off a new standard. And the idea is once we get it down and we get it settled, we can combine things back together and merge them back together in OpenMP4. So this was the thought. Meanwhile, along came Intel with their desire to build an accelerator too. They saw GPUs were becoming really important in computing, and they said, what can we do? Well, Intel's philosophy has always been, when they see a new technology, how can we do this with x86, with our Intel processors we know how to make? And so they've been pretty successful with that over the years. When RISC chips came along, they said, how can we roll RISC into our processors? And so with this, they said, how can we make GPUs with Intel processors? Because our expertise isn't making thousands of processors, or back then hundreds of processors like NVIDIA does for their GPUs, for their video game GPUs, but we do know how to make a really smart processor, and we could probably put dozens and dozens of them on a card. So that was their idea for an accelerator. They called this the many integrated core product, and they sold an accelerator card. So this is a card you could plug in based on having a bunch of x86 things. People thought of them as kind of being like Pentium type cores, but they actually had better math instructions. And so this was this was the first microarchitecture that they had, was this ring bus connecting 60 of these Pentium-like GPUs. This was the last version before they kind of pulled the plug on the line, which is the Knights Landing. And these are still in use on some big machines out there. You'll see them on that top 10 list we mentioned. There are a few Knights Landing based machines there, but they pulled the plug on it eventually. And the idea was to have in this case, it had, instead of a ring bus, it had a big tile, 2D layout, 2D array layout. And it was a bunch of these cores. So it wasn't thousands of cores. It was, 60 plus cores, depending on the version. But the cores are smarter, and more powerful per core than the simple-minded cores on a GPU. So that was Intel's approach. And because of that, they have a lot of influence on the OpenMP spec. Intel has always had a lot of influence because they make the most popular multi-core processors, right? So they use their influence to make OpenMP spec work as well as possible with their type of accelerator. So OpenMP4, which was supposed to be this accelerator-based OpenMP, became much more friendly to using multi-core devices like their Intel accelerators. NVIDIA, meanwhile, had an awful lot of influence over the OpenACC spec, as could be expected, and they pulled OpenACC towards being more and more effective with their devices. So what happened was, when the merger was supposed to happen here, it didn't happen. Instead, the two specs had pulled apart, and there is still hope that somewhere down the road, things may merge back together. But at the moment, the technical differences between these two have grown to where it's not a trivial thing to reconcile the two. We can see that the way OpenACC has these asynchronous queues defined works great with GPU type devices. The way OpenMP has things based on these tasks, these more flexible tasks that can be independent, works better for CPU cores. And so OpenMP4 did not merge things back together, but they did go and say, okay, we're going to start supporting accelerators. We need to have some memory management at least, because this device, this Intel accelerator, is on the PCI bus, has its own memory, separate memory. So they're CPU cores, but they have a separate memory from the main CPU. So they had to add into OpenMP4 the memory management kind of commands that OpenACC has, and they did. And as we look at it, we'll see that they are very similar in functionality. At first glance, they seem like different words, but they do the same kind of thing. So in OpenMP now, we have these additional commands that can target a device, and that means something with a different memory space. And the devices are numbered. So this saying target device 0 is a way of saying target accelerator, the first accelerator. And instead of having copy commands, we have map commands. So map to from of B says take the B array and map it to and from the memory space on this device. So this is the equivalent of copy, right? Because copy is copy in and out. As a matter of fact, you can see, let me jump ahead to this one. You can see how obvious it is right here. You can see that map to is the same as copy in. Map from is the same as copy out. Map to from is the same as copy, right? So we have these ridiculously similar commands to do kind of the same functionality between the two. OpenMP has data constructs too. In OpenACC, we have data, we have target data. Enter data, target enter data. Update, target update. So OpenMP has rolled in these OpenACC kind of commands. It even has the unified shared memory thing I talked about earlier, moving stuff automatically. It even has that. It also works as well as it does on NVIDIA devices, which is terrible. We have compute constructs in OpenACC. We have parallel loops and kernels. In OpenMP, we just stick target in front of our regular do loops, our regular OpenMP loop commands. We have the ability to distribute work around with our gangs and whatnot in OpenMP. We have the ability to start to distribute things around in teams and whatnot. So you're going to see very, very similar behaviors, and to the point where porting a code from one to the other is almost more like just an editing exercise than anything else. But there are some differences. As I pointed out, the way that we deal with having independent tasks on a CPU is very flexible with tasks primarily and the dependencies between them. On a GPU, because things are synchronized more, we want to work with queues. So these are some differences in the way you might write an algorithm. So the bottom line is today we have OpenMP4 on that we could technically run on NVIDIA devices. And if you do that, you will find that you end up having to target the device and distribute things in teams and whatnot. And then you can use the old OpenMP commands that we had from yesterday. But you can see it's a little bit ugly. As a matter of fact, here's a nice comparison across them. Here's OpenMP4 on NVIDIA and Phi and versus OpenACC. In OpenACC, we just use kernels directive in front of a loop. Everything works, right? In OpenMP4 for NVIDIA, we got a lot more nonsense to worry about how to distribute the work around. In OpenMP4 for Xeon Phi, it's a little bit cleaner because it targets Intel devices. So you can see the obvious bias for OpenMP towards Intel and the obvious bias for OpenACC towards GPUs. And you can try to make this work then across multiple architectures in your code. So here's those if defs I was talking about before. So if we want to write a piece of code, this for loop, and have it work on CPUs and have it work on Knight's corners and GPUs and Knight's landings, you can see you can do it by having a bunch of different directives that get used depending on what device you're on. But it gets to be pretty ugly. Also, it doesn't work so well. We do have meta directives now. So they added in to OpenMP with 5, I think it was. They added in meta directives. So you can say, okay, if I'm on an NVIDIA architecture, do this kind of commands. Otherwise, do these other commands for Intel architecture. So they started to try to get rid of some of the if defs, but that doesn't solve the performance problems. So anyway, here is where the performance issues, which is what really I think matter the most, come in. And here's a paper, a relatively recent paper, which I thought did a pretty fair investigation of this. Certainly the people involved know what they're doing. And this is where they compared a bunch of benchmarks on leadership class platforms, so some big machines, and they used different compilers, a bunch of different compilers to make sure that they were getting a fair sample. And they used OpenMP to implement a bunch of codes that would normally be done with OpenACC. And the bottom line, if you read this, is that OpenMP4 is not competitive with OpenACC performance-wise. OpenACC just works better on GPUs. Again, that shouldn't be a surprise given how the parties involved here have promoted things to promote their own interests. One interesting note in this paper, by the way, is that they did use both kernels and lower level loop commands because they know what they're doing to make sure that their kernels weren't holding back the performance. And they found kernels these days works pretty well. So as of when this paper was written, they had a hard time beating kernels performance with their own lower written loops, to go back to a topic we were talking about earlier. But at any rate, at this point in time, if you're using an Intel accelerator, which is probably unlikely, like I say, they're kind of defunct, then you're going to use OpenMP4 to do the data management. Otherwise, if you're using an NVIDIA GPU, you're going to want to use OpenACC because, again, no surprise, NVIDIA and OpenACC are pretty close together. And that's just the reality. Now, it's not a terrible bummer in the sense that should things change in the future, or should you have to change from OpenACC to OpenMP or vice versa, you can see now, knowing both of them, that they're very, very similar in capabilities. You're going to spend some time screwing around with an editor more than anything. So at this point, the thing that makes the most sense, use OpenACC to do your GPU computing, because it will work and it will work properly right now. And if 3 or 4 years from now, OpenMP catches up to OpenACC and you decide you just want to use OpenMP across the board, you can see you're going to spend some time just translating, with your text editor, searching and replacing some commands. But right now, using OpenMP 4 to try to do GPU computing is an exercise in poor performance and frustration. So that's the situation. It's unfortunate that this is the way the industry players have pulled things, but that is the reality, and I don't want you to go off unprepared and waste time. The national labs have decided that to deal with this by adding one more layer on top of this. And so they now have this one API framework, which now spits out beneath it code, OpenACC code or OpenMP code. And I find that to be an incredibly distasteful, awful way to deal with this problem. But that's the way they're dealing with it right now. I don't think one API is going to stick with anybody, because it is very, very ugly and one more layer of nonsense to support. But that's their approach at the moment. Or COCOS. COCOS is that's a sign of how unstable these approaches are, is that they have multiple approaches at the same time to do the same thing. So you can use one API, which will spit out the right code underneath it, or you can use COCOS and it'll do the same thing. Or which one should I use? It depends on whose machine you're on. So instead, I suggest stick with the standards that are well established. Use OpenMP for multi-core, use OpenACC for GPU, and you won't have any unpleasant surprises, at least. Okay, so that is it for that topic. And I hope you can see that these things tie together, and I hope you feel comfortable moving back and forth between OpenMP and OpenACC. You can see a lot of the principles are very much the same. Let me catch up on questions now. Let's see. OpenACC works more efficiently with NVIDIA accelerators, and OpenMP more efficiently with Intel accelerators. Yes, that's exactly what I mean. New OpenMP loop streamlines things quite a bit. Well, loop isn't a new thing in OpenMP. It's definitely, we just didn't, we did talk about it yesterday in the advanced OpenMP stuff. We didn't spend a lot of time with it, but it was there, which will be the future winner amongst OpenACC and OpenMP. At this point in time, I mean, it is hard to tell, but at this point in time, it seems like OpenACC is going to continue to dominate the GPU world, and OpenMP is going to continue to dominate the CPU world. And I don't see one of them, and they both hope that they overtake. They both hope, OpenACC hopes that you do all of your CPU programming with it as well. And OpenMP would like you to do all your GPU programming with it as well. But at this point in time, they're just not good. They're not competitive in their cross domains. So on paper, you could use either one to do everything. But in reality, at this point in time, neither one is got an advantage in its opposite domain. So it's hard to say. Again, it's a slight annoyance. Once you see how similar they are, it's not a killer deal. It's not like you're rewriting your code all the time, but it is slightly annoying. So to have to use two when they should have merged long ago, but I don't see that happening anytime soon. But you can. So the next question, can we use both of them at once? Absolutely. Absolutely. There's no problem with mixing both. They are. So the standards committees, as much as I resent the influence of the industry players in keeping the things from merging, the standards committees themselves have been professional, and they both work very well with each other. So they're not some weird competitive thing where they try to break or handicap or sabotage the other. OpenMP and OpenACC work very, very well with each other at the same time. So you can use OpenMP to do multi-core computing and use OpenACC to control the GPUs. As a matter of fact, that's what everybody does, and that works just great. So the two standards work very, very well with each other, and you can have both sets of pragmas and have them both active at the same time. We'll come back to that topic specifically when we talk about hybrid computing later on, because we will find ourselves wanting to use all MPI, OpenACC, and OpenMP at the same time to make all the machine hum, well, and they work just fine with each other. So they don't sabotage each other; they just have it merged together. And you would use both flags to activate both of them. Let's see. It's possible to parallelize one loop with both OpenMP and OpenACC working together. Well, not together. You pick one or the other. So if you've got a loop, either you're going to run it with OpenACC on the GPU, or you want that loop to run on the CPU. And whichever one you think it belongs on, you can use the appropriate directives. So if you've got a loop that's doing GPU amenable stuff, you probably want it to work on the GPU. Maybe you got a loop that does some really odd serial recursive thing in small chunks or something, and you want it to run on the CPU. You would do that with OpenMP. So you have no problem, but you just can't, a loop can't work on both at once. And Warren mentions on MATLAB with GPU. Well, MATLAB, you hope that the MATLAB routines that you're interested in run well on the GPU. So MATLAB's put a lot of effort into making things work with GPUs. They've had to, because it's very important. And you just hope that things automatically work well with the GPUs. Are AMD chips compatible with OpenMP? AMD processors are completely compatible with OpenMP. No problems whatsoever. It's the standard way you program them. AMP accelerators, as in GPUs, have varying degrees of compatibility with OpenMP and OpenACC. So that's one of the reasons NVIDIA is such a toehold in this market, is they make sure their stuff works really, really well, and it does. AMD's been chipping away at it and changed their mind a couple of times on how you should program their devices. So at one point in time, it was OpenCL, and then they changed that to their own ISA, their Fusion ISA, which was different. And now they're, I think, mostly on the OpenACC bandwagon. But they've changed their mind, and it's kind of cost them a little bit. So people that spent time using OpenCL a long time ago are not thrilled right now. Simple programs like Excel use CPUs and GPUs natively without any additional programming. It is, I think a lot of people think it's overdue for applications to say, hey, if there's a GPU here, I should utilize it. But more and more it's happening. As a matter of fact, you will find that most, for example, Photoshop these days absolutely will leverage the GPU very, very heavily to do all kinds of image transforms and everything. So more and more applications are using automatically GPU resources if they're there, and multi-core resources for that matter. It wasn't that long ago that you have a multi-core machine and you'd say, well, but none of my video games run multi-core. Now all the video games are multi-core. Video games always use GPUs, but for video. But now things like Photoshop will use GPUs for processing and more than just video. So gradually applications are realizing that the future has been parallel for so long that they had best get on board. So Excel is an interesting case. I know people that do massive spreadsheets in Excel with lots of VBA programming, and to the point where it takes hours sometimes for them to run calculations. I bet you they would be thrilled if Microsoft decided to GPUize their code. Are there practical hardware considerations to how Bridges is organized? There are a ton of practical considerations as to how you distribute your GPUs, what kind of CPUs they're attached with, how much memory. It's in our case, we have a huge effort goes into designing the machine to accommodate a particular mix of applications, which is all over the place. Some people's applications benefit from one configuration, other people from other different configurations. Some people need massive amounts of high-speed disk attached or SSDs, and other people don't care about that part of the machine. So that's why Bridges has a diverse mix of things in different pieces, and we still can't make everybody happy. AWS has certain configurations that they find to be really popular that they will offer you with the cloud, but I can guarantee you other people are like, why don't you have this configuration? So it's a battle to match applications. We target Bridges towards big data analytics a whole lot, but we still have lots of other generic science running on the machine. Other machines in the XSEDE constellation have other specialties to them. So there's no one size fits all, but everybody's trying to do their best to address their target audience. But it makes a big difference, configuration. What happens if both instructions are applied to the same loop? Well, your compiler will complain because it's either trying to generate a GPU kernel for it, or it's trying to generate OpenMP directives for it. Let's see. It's not clear in considerations how to go for CPU OpenMP or GPU OpenACC parallelization my code. Machine to run on the algorithm. Well, first of all, nothing says you can't do both. As a matter of fact, you can see sometimes it's easy enough to do both just to try it out and see which one's most effective on the hardware you have at hand. So, I mean, you can see some of these loops we've done, right? I hope you realize, oh, I could in an afternoon, try both and see which one works best. Is this code really good on a GPU or really good on a CPU? Now, with some experience and some expertise, you can often take a pretty good guess at what works where. These days, GPUs are in all of these big machines. Big supercomputers also works at, because GPUs have taken kind of a good lead on many, many different classes of problems. So these days, the generic philosophy is if you can make it run on a GPU, do it, because that's probably your best win. But that's not always true. But I hope you say, wow, I'm competent to try both. I understand both tools. And you can say, okay, let's take a couple loops in my code that are important to me. Let's try both and see if this GPU, now that of course assumes you've got a particular configuration. Maybe your GPU is not so good. Maybe your CPU is not so good. So you can't do one test somewhere and say that's the answer. But I hope you feel like experimenting a little bit isn't an impossible task. You can throw some directives, be they GPU directives or be they CPU directives, at some loops and see what happens. And again, it depends a lot on the algorithm. It depends also on your hardware. You know, if you've got a $4,000 GPU, it's going to work a lot better on a GPU, amenable code than some built-in graphics card, in your laptop. So all things considered, though, I hope you walk away from this workshop feeling competent to take a guess, but more importantly, to take a shot at things and experiment. Because at the end of the day, that's an awful lot of the times where you really find out what's up. You do an experiment and see. How to install OpenACC compiler on your laptop? Well, I would suggest probably the easiest way to go is to go to that NVIDIA free one and take a look at it. And it should have some pretty basic installation instructions there. I hope their instructions are pretty clear. I've pointed a lot of people there and they haven't come back with complaints. So I think it's pretty free. Although again, GCC, if you've got that installed, also is there. But I'll suggest the NVIDIA PGI one, just because I know it's what we've been using and works pretty well. Hope somebody already answered where to find that at least. Its principles consideration apply to external GPUs. One can customize to regular laptop. Yeah, but regular laptop GPUs, the ones that are built into laptops, are by design underpowered. I mean, literally because they don't want sucking up your battery and they don't have a way to cool them. And GPUs generate a ton of heat. I mean, I showed you that picture yesterday of somebody frying something on a CPU. GPUs generate a lot. I mean, well, you know it if you bought a GPU and you need to upgrade your power supply because it takes hundreds of watts. There's a reason for that. So your laptop GPU is underpowered in pretty much every regard. So it's as a development resource, it's great. So don't be afraid to install this stuff on your laptop and use it to investigate things and get your code up and going. But when it comes time to actually run a big simulation or whatever, you probably want to move over to some departmental resource or grab an account on a machine like Bridges. I mean, that's why XSEDE exists, because people outgrow their laptops very, very easily when they get serious. So don't be afraid to develop on your laptop, but don't take the performance at all seriously. They're just very handicapped by the power envelope they're stuck in. On the Plus example, we showed that OpenACC was the winner. It's because it's using NVIDIA machines. No, I mean, in Laplace is maybe a good generic example of GPUs these days kind of in general have the edge. If you can get something to run well on a GPU, the number of flops available, you can just see this in terms of maximum teraflops from a good GPU these days are 10 plus teraflops per GPU. CPUs have a hard time reaching that. So if something runs well on a GPU, that's probably the best device in general. It's hard for a CPU to beat something that fits well on the GPU. And that's just the general theme of the past 10 years has been, if you get something to run well on a GPU, that's going to be your most competitive device. And Laplace fits into that class. It's not universally true, but it's a good example. GPU in terms of reducing data load, store time. Integrated GPU, no, integrated GPUs still typically, so the ones that are totally integrated, like on chip, are pathetic at doing any kind of scientific computing. And so they're awful. So their transfer times, they might even share memory. So there are GPUs and video game consoles and whatnot that share memory. You might think that's the best thing of all, they share memory, but they share slow memory. They don't have the high bandwidth memory. So integrated CPUs are typically not very serious. The separate ones, cards, they are very serious because they can stick in that high bandwidth memory, which is where most of the performance capability comes from. And you can't stick that in a little integrated GPU. On Bridges to run a GPU code, one should use the GPU nodes. That's the only place to run. So that's why we have special GPU nodes, the pool of GPU nodes. That's where you want to run. Other nodes don't have the GPUs in them. And that's true of most of the big machines. You'll see they'll have a GPU pool for GPU codes, and they'll have a CPU pool would have maybe even better CPUs for the CPU driven usage. GPU time cost the same as the CPU time cost. They actually are allocated separately. So if you ask for time on bridges, you ask for either a GPU time or for CPU time. So the service units, as they call them, that's the way that they build things. You're given free service units. The service units are separate for GPUs and CPUs because those are two different classes of resource. So when somebody asks for time, you can ask for one or the other. You can ask for both, but you're given two separate accounts, those two things. How do CPUs and GPUs compare in total number of transistors and power dissipation? That's really the million-dollar question behind all the things of should I use a CPU or GPU or which one's better. People building the machines, that's actually the kind of question they ask. They say, okay, power dissipation, which one gives me the most flops? And these days you get the most flops per watt out of a GPU. And that's actually been true since the beginning of GPUs. That's why people embrace them. So GPUs have a big substantial advantage in flops per watt. Okay, and then you might say, well, that's the answer then. Why does anything but GPUs exist? Well, you can see GPUs are limited to types of problems. They have to be these very regular types of problems, and CPUs still have a role. There are many, many problems where CPUs and their more flexible cores and logic work. And so even though CPUs have been losing and continue to seriously lose the flops per watt battle, their flexibility means that they're still desirable and necessary in lots of contexts. And you can see this in the top 500 list. Again, go and look at it. And you can see, you can even go historically. That site's pretty neat. You can see historically back and forth, and you can see how things have changed. And you can see that as GPUs became available, they've slowly expanded more and more and more of the machines, to the point where all the big machines, including the exascale machines we talked about this year, most of their flops, most of their capability is in their accelerators, in their GPUs. So that's what slowly happened. Is the argument is just that the GPUs have become more and more of where you want to spend your money, but you still need, nobody's built this an all GPU machine though, because you still need the CPUs for the things that GPUs aren't good at. So it's balanced, but it's shifted pretty much towards GPUs slowly over time. The total number of transistors, these days, the number of transistors in the device is probably dominated by the RAM more than anything else. So it's memory size. So if you really say, the CPUs have a lot of transistors, but the total motherboard with the CPU and its memory is more transistors altogether than the GPU and its memory. So it's a hard thing to compare just the transistor count because the memory is a big part of it, and the CPUs have more just memory. Do we need CPU? We have cheap GPU. Well, like I said, yeah, you might think that, but there's a lot of problems then that GPUs don't run well, and that's where CPUs are absolutely necessary, or pieces of problems for that matter. When you get to a large serious code, there are just parts of it, initialization and setup stuff and IO and everything, where the CPU is more than a trivial part of the work. So you need those CPUs. A large hybrid code to make it efficient on GPU nodes, all the OpenMP blocks need to be replaced. No, I mean, the OpenMP pieces may be the things that run most efficiently on the CPU. I mean, hybrid codes exist for that reason. There are things that run well on CPU, and those loops should stay there. And so now you have the tools to make the experience judgments. Instead of a lot of people, they only know how to do GPU programming or CPU programming, or whatever. And when all you have is a hammer, every problem looks like a nail, right? So they're forced into one path. You've now got the ability to use both tools. So you can look at a loop and try both things and say, or even in advance, sometimes know, hey, this loop is small and has lots of conditionals in it. Right away, if I see a piece of code, it's got a lot of conditionals going on and things, I go, that's not going to work on a GPU so well. Might be great to parallelize that on the CPU. All right, look at something as a big matrix operation. Wow, if I can get that to run on the CPU, that's going to be great. And then add in the memory transfers back and forth, change the picture a little bit, so I can make an assessment in advance. You can also experiment, kind of, painlessly. Now you can see it's not that hard with these directives to experiment either. But there's no general just, hey, GPUs are great for everything, or I've got a hybrid code. All my loops should be on the CPU or the GPU. Let's see. Okay, I think we've, with that, caught up on all the questions. How are we doing for time? I've lost track of my clock. We're doing great on time. So I can hang around. Like I said, today's probably the most mellow day. So I can continue to answer questions until it comes to a complete halt, in which case, so those of you that have other things to do, feel free to leave. You're not going to miss any more content. We've covered everything we're going to cover for today. Those of you that want to ask questions, here's a good chance to ask open-ended questions, a good open-ended Q&A session. But those of you who want to leave, we'll see you sharply back here tomorrow morning. We're going to get started on time because tomorrow is a very, very different direction with this stuff. We're going to take MPI. That's the way we can get ultimate scalability, but with a very different approach. The theme of the past 2 days has been, wow, aren't OpenMP and OpenACC, don't they share a lot? That's pretty cool. We can take advantage of that. With OpenMP, or excuse me, with MPI, we're going to find ourselves in a very different mindset. It's going to be a very, very different approach to things. And so we're going to start with that tomorrow morning for those of you that want to take off. So we'll see you later. Have a good day. Otherwise, I'll hang out until the questions are exhausted, which might already be now. So moving data from disk to CPU, yeah, that's or to GPU. Usually that goes through the CPU. That's one of the things the CPU does is deal with I/O systems and disk systems and move data around. And overlapping that can be very effective too. In the machine learning world, for example, it's neat to be able to have the CPU go read stuff off disk, translate it and format it and everything else from the file format it's in, and get it in just the right form so that when it shoves it across memory to the GPU is ready to go at it and do its machine learning. And then you can even overlap that communication and computation. So the GPU and the CPU are great partners a lot of the times in machine learning tasks. You're reading in an image and it's a JPEG file. Well, the GPU wants it in some other format. The CPU can do all that conversion and shove it across the PCI bus, and the GPU can just look at one picture after another very efficiently because the CPU is doing all of that work. PCI buses are bidirectional, so but the bandwidths are specified bidirectionally usually. Can I suggest any free online courses to further the concepts taught today? It's a good question. I'm sorry I don't have a good answer. There are a lot of resources. I'm trying to think of one that dovetails with what we've just done here. A lot of people just jump from here right back to their application. I hope I've left people prepared to feel like they can at least begin to jump on an actual application. That's how I hope I've taken people that far by the time we're done. And so beyond that is a lot of expertise, in documents, things like that. So I don't want to point you at a tutorial because we've already covered the basics. So I'm having a hard time thinking of a great online thing that just follows up on what we did. I can say that if you go to openacc.org or openmp.org, they should be a good place for you to see what's a good starting point, at least to see what's available out there in terms of follow-ons and tutorials and whatnot. So, and let me know if you really feel like you're lost, there isn't a good resource, and I'll poke around for something if you let me know what level and what focus you're interested in. I think going beyond this, it's kind of important for me to say, what is your focus? What is your area of application? What are you really trying to do before I can say that more advanced material is not a waste of your time. Just getting the C programming, preferred IDE, plant, etc. That's a good and controversial question. And you're lucky that the controversies, because there's so many good ones around these days. People, somebody earlier said they're doing this, they're using Visual Code Visual Studio Code to do things remotely with that IDE. That's a very basic but friendly kind of editor to do things. It doesn't have a great debugging IDE built into it, but it's basic. Cost is no object. Microsoft Visual Studio, and I'm generally a huge fan of Microsoft, but their Visual Studio IDE has a great integrated environment for C code and debugging. It's got a great debugger built right in. It's very friendly. So I'm a fan. If you said to me, just cost is no object, I'm new to C or C++, and I just want to have a good IDE to make life friendly on me, Visual Studio, which is different from Visual Code. They're both Microsoft things. Hard to argue with that as a friendly IDE. But the world's got a lot of IDEs these days and a lot of preferences. And a straight text editor is never a bad way to not get distracted either when you're learning. You just have a text editor that does some basic syntax highlighting or whatever. Can't argue with that and not getting in the way. But it's also nice to have an integrated debugger. So it's I'm sure probably the chat will light up with suggestions out there since you've thrown that up. Let's see. Matter of fact, let's see. It's already starting to scroll. So I hope those are a couple initial suggestions, but also don't hesitate to try something and say, try a few different things and see what appeals to you. It's never a bad idea either. These days, IDEs are all simple and friendly to learn. They take more time to install than they do to actually get up and going with. running the CUDA FFT example. I hope the slides instructions are still up to date. If the module changed, something may have changed a little bit. If not, go back to the NVIDIA page. I have the link there and get the updated. I haven't updated that slide in a couple of iterations of this talk, and the libraries and the modules may have updated since. So go back if you want to run the CUDA FFT example. That, like I say, isn't mine, it's an NVIDIA one. I would go back to NVIDIA to start with and grab it. Grab a fresh copy from NVIDIA, and it's likely to not have any library version problem or whatever, which my old version sitting around may. And I recommend a boot camp with a finance focus. I'm not aware of one. So we have lots of finance people cross our paths and come to these things, especially the big data one. And I think that's because there may not be something that's out there just with a finance focus. It's a very active area, but I don't know of anything that caters directly to it. Is an MPI equivalent to communicate between GPU nodes? There is MPI to communicate between GPU nodes. So that's what's typically used. And we'll talk about that a little bit. So CUDA direct, and so we'll get to it, but MPI is usually used for multi-GPU node communication. And it's optimized for that too. We'll see that. Given a choice between, well, if they're statically declared, so you're saying you declare, so I'm assuming by your declaration here, you actually mean like an allocation of allocating the array as NX, NY, and Z in place, or declaring it as a separate statically allocated array as NX, NY, and Z. They will be exactly the same because they're contiguous in memory for both cases. So that's good. It's when you get to dynamically allocating them, it gets painful because to do multi-dimensions. But if you allocate, yeah, X times Y times Z bytes in memory, that's contiguous. And if you do a static allocation like this of double X, Y, Z in memory, that'll also be contiguous. So from OpenACC's perspective, they're exactly the same thing. So they're both good. Data transformation like a map function, more sort of the CPU. Well, a generic map function, it's just to say, let's say we're doing a map function where we're just mapping every element to 2 times its value. That would be great for a GPU. That's a very regular operation. But let's say we're doing a map function that's got some conditionals in it. We've got map, if something's got uppercase letters in it, change them to lowercase. If it's got asterisks and underscores, though, change those to blank spaces, right? Which is another valid map. So if you've got a map with conditionals in it that's doing funky stuff, then that's a job for a CPU. But if I've got a map that's doing a very regular transform, then it's hard to be argued with a GPU. And most maps are probably that second case. If there are several video cards in a node, is MPI necessary to make the code efficient? No, not in that case, because we can do what we did here with saying you just change the device number and the CPUs or shuffle the data off to the multiple GPUs. So if you're just working on a single node to communicate between those GPUs, you don't need to bring MPI into the mix at all. You can just make sure the CPUs divide the data up between the GPUs and shuffle it back and forth. We'll use bridges for scientific visualization. The overhead is on GPU or CPU. Well, doing remote visualization from bridges is a tricky subject. So it depends on the package and what you're trying to do. Are you trying to do it in real time over an X Windows connection? You know, it's or use some kind of funky Wayland thing. So it's very hard to answer that question in a generic way. It depends on very much on exactly what you're trying to do and which libraries you're trying to do and how you're trying to do it. And the truth is, most people doing visualization will spit things out into files, the data, to disk is their visualization, and just bring the file back and as a visualized rendered entity using something like Visit or Paraview or something, and they won't try to do it interactively in real time. So it depends on which case you fall into. And you're all very welcome. Thank you for your appreciation. You're all of you are very welcome. A good resource to do parallel work in R. I come across R and fragments of R quite a bit, but I am not an R expert. I know that R has a very healthy, concurrent programming community, both from MPI, R interface stuff I see to all the concurrent stuff we talk. But I am not an R expert, so I won't pretend to give you any advice there because I'm afraid my perspective would be wrong. So. All I can say is there's a lot. R has certainly a very healthy, robust, parallel concurrent programming environment and ecosystem. How long does it take to get approval for an allocation of PSC? For a startup allocation, it takes a couple of days, which is enough to get started, and maybe even depending on what your work, get finished. If you're doing something that's much more involved and needs a larger resource, then it's a quarterly application process. So usually people will ask for a startup to get going and then do a quarterly as soon as they have some idea of how much time they'll actually need. So if you need less than say 50,000 CPU hours, you could ask for startup and you'll have it, within the week, certainly. If you ask for a bigger amount of time because you need it for your full research, then the proposal process is every quarter. And the idea is the startup should be able to get you to the beginning of the next award. Are the codes are you protected? Yeah, and we've got standard. They're protected as far as we've got standard Unix file permissions on this. And so most people who are concerned about keeping their code proprietary set the permissions so nobody else can see what they're doing and what they're up to. So that's as far as we go. We don't enforce some kind of uber protection beyond that though. But that's sufficient for almost anybody that doesn't have government mandates like some kind of HIPAA requirements or something. Well, once again, thank you all. I'm glad you appreciate the workshop and are finding it useful. And if we don't have any more questions for today, then I will let Steve and Tom go, and we'll see you back here tomorrow.